We look out at the stars, searching for meaning. But what if the answer isn't in what we see, but in how we're shaped? Not by matter, but by space itself. Is the universe flat? Or is the world we live in curved, like a dream we've never noticed? Tonight, we drift across the fabric of space to find out. When we gaze up at the night sky, we're not just seeing points of light scattered across darkness. We're looking at a pattern, a structure, a shape that contains everything we know. From the earliest days of human civilization, we've wondered about the form of our reality. Ancient cultures imagined the world as a flat disk or a sphere carried on the back of giant creatures. Modern science has taken us further, revealing that the shape of our universe is both simpler and stranger than we could have imagined. Imagine standing on a beach at night, watching the stars shimmer above the dark water. The horizon curves away from you, a gentle reminder that we live on a sphere. But what about the space above? Does it curve too, in ways our eyes cannot perceive? When we look at distant galaxies, are we seeing them as they truly are? Or is their light being bent along cosmic curves that stretch across billions of light years? What does it mean to ask if the universe is flat? It's not like questioning whether the Earth is flat. We know our planet curves into a sphere, but the cosmos itself might follow different rules. When cosmologists talk about universal flatness, they're asking about the geometry of space-time itself, the invisible fabric that holds stars and galaxies in place. The question stretches back through time, to the ancient Greeks who pondered geometry and the stars. Euclid's straight lines and perfect triangles described a flat world that made sense to human minds. But as we ventured further into the cosmos, we began to suspect that space might not follow these simple rules. Einstein showed us that gravity isn't a force pulling between objects, but a curving of space-time itself. The sun creates a depression in the fabric of reality, and Earth rolls around this curve like a marble circling a funnel. Close your eyes for a moment and imagine. If you travel in what seems like a straight line forever, would you eventually return to where you started, as if walking around the surface of a vast cosmic sphere? Or would you continue outward infinitely, never crossing your own path? This is the question of curvature, of whether space itself closes back on itself or stretches endlessly in all directions. The answer is hidden in light. Every beam of starlight that reaches our eyes has traveled along the contours of space-time itself. Like water flowing downhill, light follows the path of least resistance through the cosmos. By observing how light moves, bends, and spreads across vast distances, we can begin to understand the shape that contains us all. Consider a triangle drawn on a flat piece of paper. Its angles always add up to 180 degrees, but draw that same triangle on the surface of a sphere, like our Earth, and suddenly the angles sum to more than 180 degrees. Draw it on a saddle shape, and they sum to less. By measuring triangles formed by distant galaxies and beams of light, astronomers can test the geometry of space itself. There's something poetic about this quest. We are tiny beings on a small planet, yet we reach out with our minds to grasp the shape of everything. We use mathematics, a language invented by humans, to describe realities that exist whether we perceive them or not. The universe doesn't care about our equations, yet somehow our equations manage to describe the universe with astonishing accuracy. Tonight, we'll explore the meaning of flatness. We'll drift through curved spaces and follow the paths of light across billions of years. We'll examine the evidence for different cosmic geometries and consider what each might mean for the past and future of our universe. We'll ponder what it means to exist in a reality whose very shape might be beyond our direct perception. The stars above us now are the same stars that guided ancient sailors across vast oceans. They're the same stars that inspired poets and philosophers to contemplate our place in the cosmos. But our understanding has deepened. We now know that some of these points of light are not stars at all, but entire galaxies, collections of billions of stars so distant that all their light merges into a single point from our perspective. And beyond the stars and galaxies lies the cosmic microwave background, the oldest light in the universe. This faint glow, invisible to human eyes but detectable by our instruments, comes from a time when the universe was young, just 380,000 years old. It carries within it clues about the shape of all things, if only we can learn to read them correctly. As we begin this journey, remember that we're not just observers of the cosmos, we are part of it. The atoms in your body were forged in ancient stars. The rules that shape space itself also shape you. To understand the form of the universe is to understand something profound about ourselves and our place within the great cosmic pattern. The question of flatness isn't just academic. It touches on the beginning of time and the end of all things. In a curved universe that closes back on itself, space is finite. It had a beginning and may have an end. In a flat or negatively curved universe that extends forever, infinity becomes real, not just a mathematical concept. The implications stretch beyond physics into philosophy and even spirituality. So let us begin our drift through the geometry of everything as we ask the deceptively simple question, is the universe flat? Let your mind expand with the cosmos as we explore the shape that contains us all, the form that defines reality itself. In understanding the geometry of space, we may come to better understand our own place within it, tiny beings contemplating vastness, fleeting creatures pondering eternity. A flat universe isn't simple, it's subtle. It hides its shape in the paths of light. When we speak of flatness in everyday life, we often think of a piece of paper, a smooth tabletop, or a still lake on a windless day. These surfaces have no bumps, no hills, no valleys. They extend in 2 dimensions with perfect evenness. But cosmic flatness is something else entirely. It's about the geometry of space-time itself, the fabric of reality in which we all exist. To understand what it means for the universe to be flat, we must first understand a bit about geometry. More than 2,000 years ago, the Greek mathematician Euclid laid out the foundations of what we now call Euclidean geometry. He described a world where parallel lines never meet, where the shortest distance between 2 points is always a straight line, and where the angles of a triangle always add up to 180 degrees. This is the geometry most of us learn in school, and it describes a flat space. Imagine drawing 2 parallel lines on a piece of paper. No matter how far you extend them, they remain the same distance apart, never converging, never diverging. Now imagine a beam of light traveling through space. In a flat universe, 2 parallel beams of light would behave just like those lines on paper, maintaining their separation across the vastness of the cosmos. But what if space itself isn't flat? What if it curves and bends like the surface of our planet? On Earth, lines that begin as parallel, such as longitudinal lines starting at the equator, eventually meet at the poles. This is the nature of positively curved space, like the surface of a sphere. In such a universe, parallel light beams would gradually converge, eventually meeting after traveling across enormous distances. Flatness in cosmology doesn't mean that the universe is 2-dimensional, like a sheet of paper. Rather, it describes the geometry of 3-dimensional space, or more accurately, 4-dimensional space-time. A flat universe still has depth, still contains objects like stars and planets, still allows us to move freely in all directions. The flatness refers to the underlying geometric rules that govern how things move and interact within that space. Think of it this way. If you were a 2-dimensional being living on the surface of a sphere, like a character in a drawing on a basketball, you might not realize your world is curved. Everything would seem flat from your limited perspective. But certain clues would reveal the truth. If you drew a large enough triangle and measured its angles, they would sum to more than 180 degrees. If you traveled far enough in what seemed like a straight line, you might eventually return to your starting point. Similarly, we 3-dimensional beings might not directly perceive the curvature of our space. We need to look for subtle clues in how light travels, in the distribution of matter across cosmic distances, in the behavior of gravity on the largest scales. One way to visualize the concept of spatial flatness is to imagine a vast cosmic grid extending in all directions. In a flat universe, this grid would have perfect right angles at every intersection, like graph paper stretching to infinity. In a curved universe, the grid would distort, with the angles between lines varying from place to place. Another way to think about it is through triangles. Draw a triangle on a flat piece of paper, and its angles add up to 180 degrees. Draw it on the surface of a sphere, and they add up to more. Draw it on a saddle shape, and they add up to less. By measuring cosmic triangles, formed by 3 distant galaxies, or by 3 paths of light, astronomers can test whether our universe obeys the rules of flat geometry. The concept of flatness is intimately tied to the density of matter and energy in the universe. According to Einstein's theory of general relativity, matter and energy curve space-time. The more stuff packed into a region of space, the more that space curves. If the universe has precisely the critical density, it will be flat. Too much density, and it curves positively like a sphere. Too little, and it curves negatively like a saddle. This critical density acts as a cosmic balance point. It's the exact amount of matter and energy needed to make space-time perfectly flat. Cosmologists express this in terms of the density parameter, omega. When omega equals 1, the universe is flat. When it's greater than 1, the universe has a positive curvature. When it's less than 1, the curvature is negative. For decades, astronomers have worked to measure omega with increasing precision. The current evidence suggests that we live remarkably close to the critical density, making our universe essentially flat, at least as far as we can measure. This flatness is one of the great cosmic coincidences that has puzzled scientists. Why should the density be so precisely balanced? It's like balancing a pencil on its point, a position so precarious that the slightest deviation would cause it to fall. The theory of cosmic inflation, which we'll explore more deeply later, offers an explanation for this apparent coincidence. It suggests that the early universe underwent a period of extraordinarily rapid expansion, which would have stretched space so dramatically that any initial curvature would have been flattened out, similar to how inflating a balloon smooths out wrinkles in its surface. But what does flatness mean for our cosmic experience? For one thing, it means that the universe likely extends infinitely in all directions. In a positively curved universe, like the surface of a sphere, space would be finite though unbounded, meaning you could travel forever without hitting an edge, eventually returning to your starting point. In a flat universe, you could travel forever in a straight line and never return to where you began. The flatness of the universe also has implications for its fate. In the simplest models, a flat universe sits at the boundary between eternal expansion and eventual collapse. It would expand forever, but at a rate that gradually approaches zero. However, the discovery of dark energy, a mysterious force driving an accelerated expansion, has complicated this picture. Even a flat universe can expand forever if dark energy continues to push outward. Think of flatness as a kind of cosmic equilibrium, a perfect balance between the outward momentum of expansion and the inward pull of gravity. This balance doesn't mean stasis. It means a particular relationship between forces, a specific geometry that shapes everything from the paths of light beams to the distribution of galaxies across the sky. The concept of flatness extends beyond just space to encompass space-time, the unified four-dimensional fabric that Einstein revealed to us. In space-time, the curvature we experience as gravity is a local phenomenon, a dimpling of the fabric caused by massive objects. The Sun creates a depression in space-time and Earth moves along this curve. But on the largest scales, when we zoom out to see the entire cosmic web, this local curvature averages out, potentially leading to an overall flat geometry. Perhaps the most profound aspect of cosmic flatness is that it speaks to the nature of infinity. In a flat universe that extends forever, there are infinite stars, infinite galaxies, and potentially even infinite copies of ourselves, living out every possible variation of our lives on planets so distant we could never reach them, even if we traveled at the speed of light for the entire history of the universe. This concept of infinity is not just mathematically fascinating, it's philosophically dizzying. If space is truly infinite and matter is distributed evenly on the largest scales, then everything that can happen within the laws of physics must happen, not just once, but an infinite number of times. Somewhere, on a planet circling a star very much like our Sun, someone very much like you is reading these words and contemplating the very same ideas. Of course, we cannot directly observe an infinite universe. Our observations are limited by the cosmic horizon, the furthest distance from which light has had time to reach us since the beginning of the universe. This horizon represents the boundary of our observable universe, a sphere centered on Earth with a radius of about 46 billion light-years. What lies beyond this horizon we cannot see, but mathematics and physics suggest that space continues, perhaps infinitely. The flatness we observe within our cosmic horizon may or may not extend beyond it. It's possible that on even larger scales, the universe has curvature that's too subtle for us to detect within our limited view. Like people living on the surface of Earth who perceive their local environment as flat because the planet's curvature only becomes apparent over large distances, we might be missing the true geometry of the cosmos simply because we can't see far enough. To truly grasp what it means for the universe to be flat, we must let go of our intuitive understanding of flatness as a two-dimensional concept. Cosmic flatness is about the rules that govern three-dimensional space, rules that determine how objects move, how light travels, and ultimately, how reality itself is structured. A flat universe isn't simple, it's subtle. It hides its shape in the paths of light that have traveled across billions of light years to reach our telescopes. It reveals itself in the delicate patterns of the cosmic microwave background, the ancient light left over from the early universe. It manifests in the Webb like distribution of galaxies across the cosmos, a vast network of filaments and clusters that emerge from the quantum fluctuations of the infant universe. As we drift through this concept of flatness, remember that we're not just describing some abstract geometric property. We're exploring the fundamental nature of the reality we inhabit, the stage upon which the entire cosmic drama unfolds. Whether flat or curved, the geometry of the universe shapes everything within it, from the grandest galactic superclusters to the quantum dance of subatomic particles. In the next chapter, we'll venture beyond flatness to explore curved spaces, those cosmic geometries where parallel lines converge or diverge, where triangles defy our Euclidean expectations, and where the fabric of reality takes on forms that challenge our earthbound intuition. If space bends, the universe may fold or stretch forever. Imagine standing on the equator of our Earth, facing north. You begin walking, carefully maintaining your direction, always moving straight ahead. After thousands of kilometers, you reach the North Pole. If you continue in the same direction, you'll begin traveling south, eventually reaching the equator again, but on the opposite side of the planet from where you started. Continue further, and you'll reach the South Pole, and ultimately return to your original starting point, having circled the entire globe. This journey illustrates the nature of a positively curved space. Although you always moved in what felt like a straight line, never turning left or right, you eventually returned to where you began. This is because the surface of a sphere has positive curvature. Parallel lines on a sphere, such as lines of longitude, always eventually meet. Triangles drawn on a sphere have angles that sum to more than 180 degrees. Positive curvature creates a closed, finite space. Like the surface of our planet, it has no edges or boundaries, yet contains a finite amount of area. If our universe has positive curvature, it would similarly be finite yet boundless. Travel far enough in any direction, and you might eventually return to your starting point, having circumnavigated the entire cosmos. But there is another kind of curvature, one that's harder to visualize using everyday objects. This is negative curvature, and it behaves in ways that challenge our intuition. Imagine a saddle shape or the surface of a potato chip. At each point, the surface curves upward in one direction and downward in another. This creates a hyperbolic geometry where parallel lines diverge rather than converge. On such a surface, triangles have angles that sum to less than 180 degrees, and the shortest paths between points curve away from what we would consider a straight line. A negatively curved universe would be open and infinite. It would expand forever, with space stretching out in all directions without limit. Unlike the finite volume of a positively curved universe, a negatively curved cosmos contains an infinite amount of space. These two types of curvature, positive and negative, represent two fundamentally different possibilities for the shape of our universe. They would create dramatically different cosmic geometries with profound implications for the nature of space, time, and reality itself. To better understand curved space, let's consider what happens to shapes within these different geometries. Imagine drawing a circle on a flat piece of paper. The circumference of that circle is precisely 2 times pi multiplied by its radius. This relationship holds true for all circles in flat Euclidean space. Now draw a circle on the surface of a sphere by marking all points that are the same distance from a central point. On a sphere, which has positive curvature, the circumference of this circle will be less than 2 times pi multiplied by its radius. The larger the circle, the more pronounced this difference becomes. Conversely, on a saddle shape with negative curvature, the circumference of a circle is greater than 2 times pi multiplied by its radius. Again, this difference becomes more noticeable as the size of the circle increases. These properties of circles in curved spaces illustrate a fundamental truth about geometry. The rules that govern shapes, distances, and paths depend on the underlying curvature of the space in which they exist. What seems like a universal constant in one geometry becomes a variable in another. Let's extend this thinking to our actual universe. If space has positive curvature like a sphere, then as we look out at increasingly distant galaxies, we should see them taking up more area in the sky than they would in a flat universe. This is because positive curvature effectively acts as a cosmic magnifying glass, making distant objects appear larger than they would otherwise. Conversely, in a negatively curved universe, distant galaxies would appear smaller than they would in a flat cosmos, as if seen through a cosmic reducing lens. By carefully measuring the apparent size of objects at different distances, astronomers can test which type of geometry best describes our universe. So far, these measurements suggest that our universe is remarkably close to flat, though small amounts of curvature, either positive or negative, cannot be ruled out. But what causes space to curve in the first place? According to Einstein's theory of general relativity, the answer is mass and energy. Matter and energy cause space-time to bend, creating the effect we experience as gravity. The more densely packed the matter and energy, the more pronounced the curvature. On the scale of the entire universe, the total amount of matter and energy determines the overall curvature of space. If the universe contains more than a critical amount of mass and energy, it will have positive curvature. Less than this critical amount, and the curvature will be negative. Exactly at the critical density, the universe will be flat. This relationship between density and curvature ties the geometry of the cosmos to its material contents. It means that by measuring the amount of matter and energy in the universe, we can predict its shape, and vice versa. For decades, astronomers have worked to inventory all the matter and energy in the observable universe. They've counted galaxies, estimated the mass of dark matter, and measured the energy of light and other radiation. This cosmic census suggests that we live remarkably close to the critical density, implying a nearly flat universe. But there's a subtlety here that's easy to miss. When we talk about the density of the universe determining its curvature, we're referring not just to ordinary matter and energy, but to all forms of mass and energy, including dark matter and dark energy. Dark matter is an invisible form of matter that doesn't interact with light, but does exert gravitational pull. It outweighs visible matter by a factor of roughly 5 to 1 and forms a cosmic scaffolding that shapes the distribution of galaxies. Dark energy is even more mysterious. It appears to be a property of space itself, a kind of negative pressure that causes the expansion of the universe to accelerate rather than slow down. Dark energy accounts for about 68% of the mass energy content of the observable universe, making it the dominant component. When all these components are added together, ordinary matter, dark matter, radiation, and dark energy, the total comes remarkably close to the critical density. This cosmic coincidence, that we live so precisely at the boundary between a positively and negatively curved universe, is one of the great mysteries of modern cosmology. To appreciate how curved space would affect our cosmic experience, let's imagine what the night sky might look like in universes with different geometries. In a positively curved universe, with sufficient curvature, light from distant objects could travel around the entire cosmos and return to us from the opposite direction. This means we might see multiple images of the same galaxy coming from different directions in the sky. The universe would act as a kind of cosmic hall of mirrors, creating an illusion of infinite space through repeated images of a finite number of objects. In a negatively curved universe, the divergence of initially parallel light rays would make distant objects appear smaller and more densely packed than in a flat cosmos. The night sky would seem to contain an even greater number of galaxies, compressed into the same field of view. Our actual observations do not show these effects, at least not conclusively. We don't see obvious repeated images of galaxies from opposite directions, nor do we see the distinctive patterns of apparent size that would clearly indicate negative curvature. This suggests that if our universe is curved, the radius of curvature must be extremely large, much larger than the observable universe. This brings us to an important distinction: the difference between the observable universe and the universe as a whole. The observable universe is the region from which light has had time to reach us since the beginning of the cosmos, a sphere centered on Earth with a radius of about 46 billion light-years. The entire universe may be much larger, perhaps infinitely so. If the universe is positively curved, but with a radius of curvature much larger than the observable universe, we might never detect this curvature through direct observation. It would be like trying to determine the curvature of the Earth while examining only a few square centimeters of its surface. At such a small scale, the planet appears flat. Similarly, if we can observe only a tiny fraction of a curved universe, that region might appear flat to all our measurements, even though the universe as a whole has curvature. This limitation of our cosmic perspective is humbling. We can only directly observe a finite region of what may be an infinite cosmos. The true shape of the universe in its entirety might forever remain beyond our empirical reach, accessible only through mathematical models and theoretical inference. Yet even within these limitations, we can explore the implications of different cosmic geometries for the past and future of our universe. In a positively curved universe with sufficient mass, gravity would eventually halt the cosmic expansion and pull everything back together in a big crunch, the reverse of the Big Bang. Like a ball thrown upward that reaches its peak and falls back to Earth, a positively curved universe might expand for billions of years before contracting back to a singularity. In a negatively curved universe, the expansion would continue forever, with galaxies moving apart at an ever-increasing rate. The cosmos would grow increasingly vast and empty, with the average distance between galaxies stretching beyond the ability of light to bridge the gap. A flat universe sits at the boundary between these two destinies. In the simplest models, without dark energy, a flat universe would expand forever, but at a rate that gradually approaches zero, like a ball thrown upward at exactly escape velocity. However, the discovery of dark energy has changed this picture dramatically. Even a flat or positively curved universe can expand forever if dark energy continues to drive cosmic acceleration. The geometry of space is no longer the sole determinant of the universe's fate. As we contemplate these cosmic curves, it's worth reflecting on how they shape our understanding of infinity. A positively curved, finite universe contains a limited amount of matter and energy. Given enough time, patterns would eventually repeat. If the universe were to last forever, the same arrangements of particles would recur, perhaps leading to identical copies of Earth and its inhabitants in the distant future. In a flat or negatively curved infinite universe, the possibilities are even more mind-boggling. With infinite space containing infinite matter, every possible arrangement of particles must exist somewhere, including exact copies of our world and ourselves. This concept, known as the multiverse of infinite space, suggests that everything physically possible is not only possible but inevitable, occurring infinitely many times across the vastness of space. These implications of cosmic geometry extend beyond physics into philosophy and even spirituality. They touch on questions of uniqueness, identity, and meaning. If identical copies of you exist elsewhere in an infinite universe, what does that mean for the uniqueness of your experiences and choices? If everything possible happens somewhere, how do we frame concepts of purpose and significance? The curvature of space also influences how we understand cosmic distances and the connection between separate regions of the universe. In a positively curved universe, points that appear far apart when viewed in one direction might actually be close together when viewed from another angle, like locations on opposite sides of the Earth that can be reached by traveling in different directions. In a negatively curved universe, the true separation between distant points would be even greater than it appears, with space stretching more dramatically than our intuition suggests. These geometric properties affect not just how we measure cosmic distances, but how we conceive of causality and connection across the cosmos. Regions that seem impossibly distant and unrelated in a flat or negatively curved universe might be intimately connected in a positively curved cosmos, with influences traveling along shorter paths than we might expect. As we drift through these curved cosmic geometries, it's important to remember that they're not merely abstract mathematical constructs. They represent genuine possibilities for the shape of reality itself. The geometry of space affects everything from the paths of light beams to the distribution of galaxies, from the evolution of the early universe to its ultimate fate. When Einstein formulated his theory of general relativity, he showed us that gravity isn't a force acting across distances, but a curvature of space-time itself. Massive objects create depressions in the fabric of reality, and other objects move along these curves. This insight transformed our understanding of space from a fixed, rigid background to a dynamic, malleable medium that bends and stretches in response to its contents. On the scale of our solar system, this curvature is subtle but measurable. Light from distant stars bends as it passes near the Sun, following the curve in space-time created by our star's mass. This effect, first observed during a solar eclipse in 1919, provided the first experimental confirmation of Einstein's revolutionary theory. On the scale of the entire observable universe, the cumulative effect of all matter and energy determines the overall curvature of space. This cosmic geometry, whether flat, positively curved, or negatively curved, represents the large-scale structure of reality itself. As we continue our cosmic journey, we'll explore how astronomers measure this curvature using observations of distant light. We'll examine the evidence for flatness found in the cosmic microwave background, the ancient radiation left over from the early universe. And we'll consider what this evidence tells us about the beginning of time and the ultimate fate of all things. For now, let us simply marvel at the profound implications of curved space. In a positively curved universe, space folds back on itself, creating a finite yet boundless cosmos where straight paths eventually return to their starting points. In a negatively curved universe, space stretches away in all directions, creating an infinite expanse where parallel paths forever diverge. These geometric possibilities remind us of the limitations of our earthbound intuition. The true nature of reality may be stranger and more wonderful than our everyday experience suggests. The universe isn't constrained by human perception or understanding. It follows its own geometric logic, a deep mathematical structure that we glimpse through observation and theory. If space bends, the universe may fold or stretch forever, creating cosmic architectures of breathtaking complexity and beauty. Through the tools of modern astronomy and the insights of theoretical physics, we continue to refine our understanding of these cosmic curves, these geometric patterns that shape all of reality. The path of light tells the story of space. Every beam carries the shape of where it came from. In the vast darkness between galaxies, photons journey across billions of light years, silent messengers carrying information about the cosmos. These particles of light travel along the contours of space-time itself, following the curves and dips in the cosmic fabric. By studying the paths of these ancient photons, astronomers can deduce the geometric shape of the universe. Light moves differently in flat space than it does in curved space. In a perfectly flat universe, light travels in straight lines that never converge or diverge. Two parallel beams will maintain their separation forever, neither coming together nor moving apart. This is the geometry of Euclid, the ancient Greek mathematician whose work defined our intuitive understanding of space for more than 2,000 years. But Einstein showed us that space can curve. In a positively curved universe, like the surface of a sphere, parallel beams of light gradually converge. They might start out moving in what seem like straight lines, but the underlying curvature of space brings them together, like lines of longitude that begin parallel at the equator but meet at the poles. In a negatively curved universe, the opposite happens. Parallel beams slowly drift apart, following the hyperbolic geometry of a saddle-shaped space. The divergence might be subtle, detectable only over enormous distances, but it would be there, encoded in the light that reaches our telescopes. This relationship between geometry and the path of light gives astronomers a powerful tool for measuring the shape of the cosmos. By observing how light behaves over vast distances, they can test whether our universe is flat, positively curved, or negatively curved. One way to do this is to study the apparent size of objects at different distances. In a flat universe, the apparent size of an object decreases in direct proportion to its distance. Double the distance, and the apparent size halves. This relationship forms the basis of perspective in art and our everyday visual experience. But in a curved universe, this relationship changes. In a positively curved space, distant objects appear larger than they would in a flat cosmos. It's as if the universe itself acts as a subtle magnifying glass. In a negatively curved universe, distant objects appear smaller than they would in a flat space, as if seen through a reducing lens. The challenge for astronomers is finding objects whose true physical size is known, so they can compare this to their apparent size and deduce the geometry of the intervening space. This is difficult because most cosmic objects come in different sizes. Stars, galaxies, and even galaxy clusters vary greatly in their dimensions. One solution is to use what astronomers call standard rulers, objects or patterns in the cosmos whose size is believed to be fixed or can be calculated from other properties. The most powerful of these standard rulers comes from the earliest moments of the universe, imprinted in the cosmic microwave background radiation, which we'll explore in a later chapter. Another approach is to use the bending of light around massive objects, a phenomenon called gravitational lensing. Einstein's theory of general relativity predicts that mass curves space-time, causing light to follow a bent path rather than a straight line. This effect was first confirmed during a solar eclipse in 1919, when stars near the edge of the sun appeared slightly out of position due to the sun's gravitational influence on their light. On a cosmic scale, massive galaxy clusters act as enormous gravitational lenses, bending and magnifying the light from more distant galaxies behind them. These lensed images form arcs and sometimes complete rings around the lensing cluster. The precise shape and size of these distorted images depend not just on the mass of the cluster, but on the underlying geometry of space itself. In a flat universe, these gravitational lenses produce distinctive patterns different from what would appear in a curved cosmos. By carefully measuring these lensed images and comparing them to theoretical models, astronomers can constrain the overall curvature of the universe. There's another way that light reveals the shape of the cosmos. In the early universe, about 380,000 years after the Big Bang, the first atoms formed as the cosmos cooled enough for electrons to bind to protons. Before this moment, the universe was filled with a hot, opaque plasma that scattered light like fog. After atoms formed, the cosmos suddenly became transparent, allowing light to travel freely. This light, released when the universe first became transparent, still travels through space today, though it has been stretched to microwave wavelengths by the expansion of the cosmos. We call it the cosmic microwave background radiation, or CMB, and it provides a snapshot of the early universe. The CMB appears as a faint glow coming from all directions in the sky. It's remarkably uniform, with a temperature of about 2.7 Kelvin, just above absolute zero. But tiny variations in this temperature, differences of only about 1 part in 100,000, reveal the seeds of cosmic structure, the earliest patterns that would eventually grow into galaxies and galaxy clusters. These temperature fluctuations in the CMB form a pattern of hot and cold spots across the sky. The typical size of these spots depends on the geometry of the universe. In a flat universe, they would have a characteristic angular size, different from what would appear in a curved cosmos. Think of it this way. Imagine projecting a pattern of dots onto a screen. If the screen is flat, the dots appear with certain sizes and spacing. If the screen is curved outward like a sphere, the dots appear larger. If the screen curves inward like a bowl, the dots appear smaller and more densely packed. Similarly, the pattern of fluctuations in the CMB appears different depending on whether the cosmic geometry is flat, positively curved, or negatively curved. By measuring the angular size of these fluctuations, astronomers can determine the shape of the universe with remarkable precision. Current measurements from satellites like WMAP and Planck, which have mapped the CMB in exquisite detail, suggest that our universe is remarkably close to flat. The curvature, if it exists at all, is less than 0.5%, meaning that if the universe is a sphere, its radius is at least 250 times larger than the observable universe. This extraordinary flatness is one of the great cosmic puzzles. Why should the universe be so precisely balanced at the boundary between positive and negative curvature? It seems like an incredible coincidence, like balancing a pencil on its point for billions of years. The theory of cosmic inflation, which proposes that the universe underwent a period of exponential expansion in its earliest moments, offers an explanation for this flatness. Just as inflating a balloon smooths out wrinkles on its surface, Inflation would have stretched the early universe so dramatically that any initial curvature would have been flattened almost completely. We'll explore this theory more deeply in a later chapter. Light not only reveals the large-scale geometry of the cosmos, but also illuminates its local structure. Every massive object from stars to supermassive black holes creates a depression in the fabric of space-time. Light passing near these objects follows curved paths, like balls rolling around the rim of a funnel. This local curvature creates fascinating optical effects. A black hole, the most extreme warping of space-time we know, bends light so severely that it can create multiple images of stars behind it, or even form a perfect ring of light if a star is precisely aligned. These Einstein rings, named after the physicist whose theories predicted them, have been observed by astronomers and provide striking confirmation of general relativity. Galaxy clusters, collections of hundreds or thousands of galaxies bound together by gravity, create even more complex patterns of light distortion. They can magnify distant galaxies like cosmic telescopes, allowing astronomers to see farther than would otherwise be possible. They can also create multiple images of the same background galaxy, sometimes arranged in stunning arcs or crosses. These gravitational lenses do more than just create beautiful cosmic mirages. They allow astronomers to map the distribution of matter, including invisible dark matter, within the lensing clusters. By analyzing how light bends around these massive structures, researchers can deduce where the matter is concentrated, even if it emits no light of its own. This technique has revealed that dark matter, which outweighs ordinary visible matter by a factor of about 5 to 1, forms a cosmic scaffolding that shapes the distribution of galaxies. The largest structures in the universe, vast filaments and sheets of galaxies separated by enormous voids, follow the gravitational blueprint laid down by dark matter. The relationship between light and cosmic structure extends to the earliest moments of the universe. The pattern of temperature fluctuations in the CMB represents sound waves that traveled through the primordial plasma before the cosmos became transparent. These acoustic oscillations, like ripples in a cosmic pond, established a characteristic scale that we can still measure in the distribution of galaxies today. This scale, called the Baryon Acoustic Oscillation, or BAO, serves as a standard ruler for measuring cosmic distances and constraining the geometry of space. By comparing the apparent size of this scale at different cosmic epochs, astronomers can track how the universe has expanded over time and determine its shape. All of these techniques, from gravitational lensing to BAO measurements, rely on the intimate connection between light and geometry. Light carries within it the imprint of the space through which it travels. By decoding this information, astronomers can map not just the contents of the cosmos, but its underlying structure. The behavior of light also helps us understand the expansion of the universe itself. When light travels from distant galaxies to our telescopes, it gets stretched by the expansion of space, shifting to longer, redder wavelengths. This redshift, first observed by astronomer Edwin Hubble in the 1920s, revealed that the universe is expanding, with galaxies moving away from each other at speeds proportional to their distance. The precise relationship between distance and redshift depends on the geometry of the universe. In a flat universe, this relationship follows one mathematical form. In curved universes, it follows others. By measuring the redshift of thousands of distant supernovae, astronomers have not only confirmed the expansion of the universe, but discovered that this expansion is accelerating, driven by a mysterious force called dark energy. This acceleration complicates the relationship between geometry and destiny. In the simplest models, a flat universe would expand forever, but at a rate that gradually approaches zero. A positively curved universe would eventually recollapse in a big crunch. A negatively curved universe would expand eternally at an increasing rate. But with dark energy in the mix, even a flat or positively curved universe can expand forever if the outward push of dark energy overcomes the inward pull of gravity. The geometry of space is no longer the sole determinant of the universe's fate. As we follow the path of light across cosmic distances, we're not just observing distant objects, we're looking back in time. The light from a galaxy a billion light-years away shows us that galaxy as it was a billion years ago. The cosmic microwave background reveals the universe as it existed 380,000 years after the Big Bang, nearly 14 billion years in the past. This time, machine aspect of light allows astronomers to study how the universe has evolved over billions of years. By comparing observations of the early universe with its current state, they can test theories of cosmic evolution and constrain the underlying geometry of space. The evidence suggests that our universe began in a hot, dense state about 13.8 billion years ago. It has been expanding ever since, cooling as it grows. The initial tiny quantum fluctuations in the density of matter have gradually grown into the complex cosmic web we see today, with galaxies clustered along filaments surrounding vast voids. Throughout this evolution, light has been our main messenger, carrying information across space and time to our observatories. Each photon that enters our telescopes has traveled a unique path through the cosmos, bending around massive objects, stretching with the expansion of space, and bringing us news of distant events. The path of light tells the story of space. Every beam carries the shape of where it came from. As we analyze this light with increasingly sophisticated instruments, we continue to refine our understanding of cosmic geometry, moving closer to answering the question, is the universe flat? The current evidence suggests that it is, at least to the precision of our measurements. But the ultimate answer may lie beyond our observable horizon, in regions of the cosmos we can never directly see. The shape of the entire universe might always remain partially hidden from us, accessible only through mathematical models and theoretical inference. Yet even with these limitations, the study of light and cosmic geometry reveals a universe of breathtaking elegance and complexity. We live in a cosmos precisely balanced between different possible shapes, a balance that has allowed the emergence of structure, galaxies, stars, planets, and ultimately life itself. As we drift through the cosmic ocean of light, we see reflections of the universe's shape in every beam that reaches us. From the subtle distortions of gravitational lenses to the ancient patterns in the cosmic microwave background, light carries within it the geometry of everything, waiting for us to decode its message. The path of light tells the story of space. Every beam carries the shape of where it came from. And in this light, we find not just information about distant objects, but insights into the fundamental nature of reality itself, the geometric foundation upon which all existence is built. The stars bend space, space bends time, and time flows through it all. In 1915, after years of intense mathematical labor, Albert Einstein completed his theory of general relativity, forever changing our understanding of gravity, space, and time. This theory revealed that what we experience as gravity is actually the curvature of space-time, a four-dimensional fabric that encompasses both space and time as a unified whole. Before Einstein, scientists followed the Newtonian view of gravity as a force acting instantaneously across empty space. The Earth pulls on the Moon, keeping it in orbit. The Sun pulls on the Earth, anchoring our planet to the solar system. These forces were thought to act through a void, a stage upon which the cosmic drama played out, but which itself remained unchanged by the actors. Einstein's insight was revolutionary. Space and time weren't simply a neutral background, but active participants in cosmic events. Matter and energy curve space-time, and this curvature guides the motion of other objects. Gravity isn't a force reaching across distances, but the effect of following paths through curved space-time. To visualize this concept, imagine placing a heavy ball on a stretched rubber sheet. The ball creates a depression in the sheet, a well of curvature. If you roll a smaller ball nearby, it will follow a curved path around the larger ball, perhaps even orbiting it. The small ball isn't being pulled by a mysterious force. It's simply following the shortest path through curved space. This rubber sheet analogy helps us picture how mass curves space, but it has limitations. Real space-time is four-dimensional, not two-dimensional. The curvature occurs in all directions, not just downward. And there is no external force like gravity pulling objects downward in the first place, as there is with the balls on the rubber sheet. In reality, mass and energy curve the very fabric of reality, changing how objects move and how time flows. This curvature affects everything, from the orbits of planets to the paths of light beams to the ticking of clocks. One of the most profound aspects of general relativity is that time itself is part of this curved geometry. Time doesn't tick uniformly throughout the universe, but flows at different rates depending on the strength of gravity, or more precisely, the curvature of space-time. Time passes more slowly in stronger gravitational fields. A clock placed near a massive object like a neutron star would tick more slowly than an identical clock far away in empty space. This isn't an effect on the clock's mechanism, but on time itself. Every process, from atomic vibrations to human heartbeats, slows down in curved space-time. This warping of time isn't just a theoretical curiosity, it's something we must account for in everyday technologies. The Global Positioning System, or GPS, relies on atomic clocks in orbiting satellites. These clocks run slightly faster than identical clocks on Earth's surface because they experience a weaker gravitational field. If engineers didn't correct for this time difference, GPS navigation would drift by about 10 kilometers each day, making the system useless. General relativity describes both local curvature, the dimpling of spacetime around stars and planets, and global curvature, the overall shape of the universe itself. These two aspects of cosmic geometry are connected yet distinct. Local curvature varies from place to place. It's strong near massive objects like stars and black holes, but weakens with distance. The space-time around Earth curves enough to keep the Moon in orbit and our feet on the ground. The space-time around the Sun curves more dramatically, bending the paths of planets and comets. Near a black hole, space-time curves so severely that nothing, not even light, can escape if it passes too close. Global curvature, on the other hand, describes the overall shape of the universe. It asks whether cosmic space-time as a whole is flat, positively curved like a sphere, or negatively curved like a saddle. This large-scale geometry depends on the total amount of mass and energy in the universe and affects the ultimate fate of all things. The mathematics that describes these curvatures is complex. Einstein relied on a branch of mathematics called tensor calculus, developed in the 19th century by mathematicians studying abstract geometric spaces. Tensors allow physicists to describe how space-time curves in all possible directions, and how this curvature changes from place to place. At the heart of general relativity is Einstein's field equation, often described as the most beautiful equation in physics. Written in its compact form, it states that the curvature of space-time equals the distribution of mass and energy multiplied by a constant. This elegant formula encapsulates a profound truth. Geometry and matter are intimately connected. The universe's shape and its contents are two aspects of a single reality. When Einstein first applied his equation to the universe as a whole, he encountered a problem. The mathematics suggested that the cosmos should be either expanding or contracting, but the prevailing view in 1915 was that the universe was static and eternal. To make his theory compatible with this belief, Einstein added a term to his equation called the cosmological constant, a sort of anti-gravity that would counterbalance the attractive force of ordinary matter and keep the universe stable. He had missed the chance to predict one of the most important discoveries in cosmology. Ironically, modern observations suggest that something very much like the cosmological constant does exist. We call it dark energy, a mysterious force driving an accelerated expansion of the cosmos. Einstein's blunder may have been prophetic after all. General relativity makes specific predictions about how space-time curves and how this curvature affects the motion of objects and the passage of time. Over the past century, these predictions have been tested with increasing precision, and the theory has passed every test. One of the earliest confirmations came during a solar eclipse in 1919. Einstein had predicted that the sun's mass would bend light from distant stars, causing their apparent positions to shift slightly when observed during an eclipse. British astronomer Arthur Eddington led an expedition to observe this effect, and the results matched Einstein's predictions precisely, making front-page news worldwide. Since then, astronomers have observed more dramatic examples of light bending around massive objects. Galaxy clusters can act as cosmic lenses, creating multiple images of distant quasars or distorting the appearance of background galaxies into arcs and rings. These gravitational lenses, as they're called, provide striking visual confirmation of Einstein's curved spacetime. General relativity also predicts that massive rotating objects drag spacetime around with them, like a spinning ball in honey. This effect, called frame dragging, has been measured by satellites orbiting Earth. The Gravity Probe B mission, launched in 2004, used precisely calibrated gyroscopes to detect this subtle twisting of space-time around our planet. Perhaps the most spectacular confirmation of general relativity came in 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected ripples in space-time caused by the collision of two black holes over 1 billion light-years away. These gravitational waves, predicted by Einstein a century earlier, compress and stretch space itself as they pass, changing distances by less than the width of an atomic nucleus. The LIGO detection not only confirmed another prediction of general relativity, but opened a new window on the universe. Gravitational wave astronomy allows us to observe cosmic events invisible to traditional telescopes, such as the mergers of black holes and neutron stars. These observations provide new tests of Einstein's theory in the most extreme environments imaginable. So far, general relativity has passed every experimental test with flying colors, from the subtle bending of light around the sun to the cosmic dance of neutron stars, from the precise ticking of atomic clocks to the expansion of the universe itself. The predictions of curved space-time match our observations with astonishing accuracy. Yet despite this success, physicists know that general relativity isn't the complete story. It describes the large-scale structure of space-time, but breaks down at the quantum level, the realm of subatomic particles. When scientists try to apply general relativity to the first moments after the Big Bang, or to the centers of black holes, they encounter mathematical infinities that suggest the theory is incomplete. Reconciling general relativity with quantum mechanics remains one of the greatest challenges in theoretical physics. Various approaches, from string theory to loop quantum gravity, seek to develop a unified theory that works at all scales, from the subatomic to the cosmic. Such a theory of quantum gravity would describe space-time itself as emergent from more fundamental quantum processes. But even with these limitations, general relativity provides our best description of cosmic geometry. It tells us how mass and energy shape the fabric of reality, and how this shape determines the motion of everything from planets to light beams to gravitational waves. When we apply general relativity to the universe as a whole, we find that the global curvature of space-time depends on the average density of matter and energy. If this density exceeds a critical value, space-time curves positively like a sphere, creating a finite yet boundless cosmos. If the density is less than critical, space-time curves negatively like a saddle, extending infinitely. At exactly the critical density, space-time is flat, following the rules of Euclidean geometry on the largest scales. Current observations, particularly those of the cosmic microwave background, suggest that our universe is remarkably close to this critical density, making cosmic space-time essentially flat as far as we can measure. The density parameter omega, which compares the actual density to the critical value, equals 1 within a fraction of a percent. This flatness presents a puzzle. In the standard Big Bang theory, without inflation, the universe would need to have been fine-tuned to an extraordinary degree in its earliest moments to produce the flatness we observe today. This apparent coincidence is one of the motivations for the theory of cosmic inflation, which proposes that the early universe underwent a brief period of exponential expansion that would naturally flatten any initial curvature. While the overall universe appears flat, local curvature varies dramatically from place to place. Near ordinary stars like our Sun, space-time curves gently. Near neutron stars, the collapsed cores of massive stars, the curvature becomes much more pronounced. And near black holes, space-time curves so severely that nothing, not even light, can escape if it crosses the event horizon. Black holes represent the most extreme warping of space-time we know of. They are regions where matter has collapsed to such density that the curvature of space-time becomes virtually infinite. At the center of a black hole lies what physicists call a singularity, a point where our current theories break down, suggesting the need for a quantum theory of gravity. The event horizon of a black hole marks the boundary beyond which nothing can return to the outside universe. It's not a physical surface, but a region of space-time where the curvature becomes so severe that all paths lead inward. Once past this point, even light is dragged inexorably toward the center. Yet black holes aren't completely black. In the 1970s, physicist Stephen Hawking discovered that quantum effects near the event horizon cause black holes to emit a faint radiation, now called Hawking radiation. Over enormously long timescales, this radiation causes black holes to slowly evaporate, eventually disappearing completely. This discovery revealed a deep connection between general relativity, quantum physics, and thermodynamics, the science of heat and energy. Black holes have entropy, a measure of disorder, proportional to the area of their event horizons. This relationship between geometry and information remains one of the most active areas of theoretical physics research. Beyond individual black holes, general relativity describes the behavior of spacetime on the largest scales. The expansion of the universe, first observed by Edwin Hubble and now measured with increasing precision, emerges naturally from Einstein's equations. Galaxies move apart not because they're traveling through space, but because space itself is stretching, carrying the galaxies with it. This cosmic expansion affects everything from the wavelength of light to the future of cosmic structure. As space stretches, light gets stretched too, shifting to longer, redder wavelengths. This cosmological redshift allows astronomers to measure the expansion rate of the universe and determine its age, currently estimated at about 13.8 billion years. The discovery that this expansion is accelerating, announced in 1998 based on observations of distant supernovae, came as a shock to cosmologists. According to general relativity, such acceleration requires either a cosmological constant, as Einstein originally proposed, or some form of energy with negative pressure. We call this mysterious entity dark energy, and it accounts for about 68% of the mass energy content of the observable universe. Dark energy complicates the relationship between the geometry of spacetime and the fate of the universe. In simple models without dark energy, a flat universe would expand forever, but at a rate that gradually approaches zero. With dark energy driving acceleration, even a flat universe will expand at an ever-increasing rate, eventually creating a cosmos so vast and empty that galaxies will lose sight of each other. General relativity also describes more exotic possibilities for cosmic geometry. In some solutions to Einstein's equations, space-time can fold back on itself, creating what physicists call closed time-like curves, paths that return to their starting points, not just in space, but in time. These theoretical structures would allow for time travel, with all its paradoxes and logical conundrums. Most physicists believe that such time loops, while mathematically possible in general relativity, are likely prevented by some as yet undiscovered principle, or by quantum effects not captured in Einstein's purely classical theory. The universe seems to protect what physicists call causality, the principle that causes must precede their effects. Another exotic possibility is the existence of wormholes, tunnels through spacetime that could theoretically connect distant regions of the universe or even different universes altogether. Like time machines, wormholes are mathematically permitted by general relativity, but would require exotic forms of matter with negative energy to remain stable. While these speculative ideas capture the imagination, the everyday implications of curved spacetime are no less profound. The time you experience, the paths you follow, even your very weight, all arise from the shape of reality around you. You don't fall toward Earth because of a force pulling you down, but because spacetime curves in such a way that the shortest path through 4 dimensions is what we perceive as falling. This reconceptualization of gravity as geometry ranks among the greatest intellectual achievements in human history. It transformed our understanding of space and time from absolute, fixed entities to dynamic aspects of a unified whole. It revealed that the universe isn't just filled with objects, but is itself a thing, with properties and behaviors governed by mathematical laws. As we contemplate the curved space-time of general relativity, we're led to profound questions about the nature of reality. If space and time themselves can bend and stretch, what does this mean for our intuitive sense of distance and duration? If the flow of time varies throughout the universe, is there any absolute measure of now, any universal present moment shared by all observers? Einstein's theory suggests that there is not. The notion of simultaneous events depends on the observer's frame of reference. What one observer experiences as happening now, another observer moving at a different velocity or in a different gravitational field might experience as past or future. This relativization of simultaneity challenges our deepest intuitions about time and causality. Yet amidst this relativity, certain aspects of reality remain invariant. The laws of physics take the same mathematical form for all observers, regardless of their motion or location. The speed of light in vacuum is the same for everyone, everywhere. And the four-dimensional geometry of space-time, while perceived differently by different observers, has an objective reality that all can agree upon once they account for their differing perspectives. This blend of relativity and invariance, of subjective experience and objective reality, makes general relativity not just a physical theory, but a philosophical framework that continues to influence our understanding of existence itself. The stars bend space, space bends time, and time flows through it all, sometimes quickly, sometimes slowly, always following the contours of a cosmic geometry shaped by everything within it. This dance of matter, energy, space, and time creates the stage upon which all events unfold, from the collision of galaxies to the beating of your heart. Understanding this dance brings us closer to answering the question that has guided our journey. Is the universe flat? To measure something as vast as space, we measure the shadows it casts. How does one measure the shape of everything? How can finite beings like ourselves, confined to a tiny planet orbiting an ordinary star in one galaxy among billions, determine the geometry of the entire cosmos? The task seems impossible, like an ant trying to determine the shape of the Earth. Yet through ingenuity, mathematics, and powerful instruments, scientists have developed methods to probe the curvature of the universe itself. The quest to measure cosmic geometry began with a simple question: is the universe finite or infinite? Does space extend forever, or does it somehow close back on itself? This question has fascinated philosophers and scientists for millennia, from ancient Greek cosmologists to modern theoretical physicists. In the early 20th century, after Einstein revealed that space could curve, the question became more precise. What is the sign of the universe's curvature? Is it positive like a sphere, negative like a saddle, or exactly zero, corresponding to a flat Euclidean space? The answer would determine not just the size and shape of the cosmos, but potentially its ultimate fate. One of the earliest approaches to measuring cosmic curvature involves studying the relationship between the distance of galaxies and their redshift, the stretching of light caused by the expansion of space. In the 1920s, Edwin Hubble discovered that more distant galaxies have larger redshifts, indicating that they're moving away faster. This relationship, now known as Hubble's law, provided the first evidence that the universe is expanding. The precise form of this relationship depends on the geometry of space. In a flat universe, the redshift increases linearly with distance for nearby galaxies. In a positively curved universe, the redshift increases more quickly with distance. In a negatively curved universe, it increases more slowly. By carefully measuring the redshift of galaxies at various distances, astronomers can constrain the curvature of cosmic space. But this method has complications. The expansion rate of the universe has changed over time due to the competing influences of gravity, which slows expansion, and dark energy, which accelerates it. To account for these changes, astronomers need to measure extremely distant objects, whose light has been traveling for billions of years, showing us the universe as it was in the distant past. Type Ia supernovae, the explosive deaths of certain white dwarf stars, provide excellent standard candles for these measurements. These supernovae all achieve nearly the same peak brightness, allowing astronomers to determine their distances with reasonable accuracy. By comparing the distances and redshifts of supernovae, billions of light years away, researchers can trace the expansion history of the universe and constrain its geometry. These observations, first published in 1998, led to the surprising discovery that the cosmic expansion is accelerating, driven by a mysterious force called dark energy. This finding, which earned the 2011 Nobel Prize in Physics, dramatically changed our understanding of cosmic evolution and complicated the relationship between geometry and destiny. Another approach to measuring cosmic curvature involves studying the cosmic microwave background radiation, or CMB. This faint glow, discovered in 1965, represents the oldest light in the universe, released about 380,000 years after the Big Bang, when the cosmos first became transparent. The CMB appears as a nearly uniform radiation coming from all directions in the sky, with a temperature of about 2.7 Kelvin just above absolute zero. But tiny variations in this temperature, differences of about 1 part in 100,000, reveal crucial information about the early universe, including its geometry. These temperature fluctuations in the CMB form a pattern of hot and cold spots across the sky. The characteristic size of these spots depends on the curvature of space. In a flat universe, they would appear with a specific angular size in our sky. In a positively curved universe, like a sphere, these spots would appear larger, as if seen through a magnifying glass. In a negatively curved universe, like a saddle, they would appear smaller. This relationship between geometry and apparent size gives astronomers a powerful tool for measuring cosmic curvature. By analyzing the statistical properties of the CMB temperature fluctuations, specifically what scientists call the acoustic peaks in the power spectrum, they can determine the overall shape of the universe with remarkable precision. The principle behind this measurement is similar to how we might determine the shape of a surface by studying how sound waves propagate across it. Sound travels differently on a drumhead than on a curved Bell surface. Similarly, the acoustic waves in the early universe, pressure waves traveling through the primordial plasma, were affected by the underlying geometry of space. These acoustic oscillations left their imprint in the CMB, creating a characteristic pattern of hot and cold spots. The first and most prominent acoustic peak in the CMB power spectrum corresponds to sound waves that had just enough time to compress once before the universe became transparent. The position of this peak on the sky directly relates to the curvature of space. Several space missions have mapped the CMB with increasing precision. The Cosmic Background Explorer, or COBE, launched in 1989, provided the first evidence of temperature fluctuations in the CMB. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, mapped these fluctuations in much greater detail. And the Planck satellite, launched in 2009, created the most detailed map yet, measuring the CMB temperature across the entire sky with extraordinary accuracy. The results from these missions, particularly WMAP and Planck, indicate that our universe is remarkably close to flat. The curvature parameter, which measures the deviation from perfect flatness, is consistent with 0 to within a few tenths of a percent. If the universe is a sphere, its radius must be at least 300 times larger than the observable universe. This extraordinary flatness is one of the great puzzles of modern cosmology. In the standard Big Bang theory, without inflation, the universe would need to have been fine-tuned to an incredible degree in its earliest moments to produce the flatness we observe today. This apparent coincidence is one of the motivations for the theory of cosmic inflation, which naturally explains why the universe appears flat. Beyond the CMB, astronomers have developed other methods to probe cosmic geometry. One approach involves studying the distribution of galaxies on the largest scales. The early universe contained sound waves that left their imprint not just in the CMB, but in the way galaxies are distributed today. This imprint, called baryon acoustic oscillations, or BAO, creates a characteristic scale in the clustering of galaxies. This scale acts as a standard ruler for measuring cosmic distances. In a flat universe, this ruler should appear the same size at all distances, once we account for the expansion of space. In a curved universe, it would appear to change size with distance. By measuring the apparent size of this standard ruler at different cosmic epochs, astronomers can constrain the curvature of space. Another way to probe cosmic geometry involves gravitational lensing, the bending of light around massive objects due to the curvature of spacetime. On cosmic scales, the large-scale structure of the universe, consisting of galaxy clusters and the dark matter surrounding them, causes subtle distortions in the images of distant galaxies. These distortions depend on the distribution of matter and the underlying geometry of space. By statistically analyzing these distortions across large areas of the sky, astronomers can map the distribution of matter and constrain the curvature of the universe. This technique, called weak gravitational lensing, is a powerful probe of both cosmic structure and geometry. One particularly elegant way to test cosmic geometry involves triangles. In Euclidean geometry, the angles of a triangle always sum to 180 degrees. In positively curved space, like a sphere, triangles have angles that sum to more than 180 degrees. in negatively curved space, like a saddle, the angles sum to less. Astronomers can measure cosmic triangles using distant quasars or galaxies as the vertices. By carefully determining the angles between these objects as seen from Earth, they can test whether the universe follows Euclidean geometry on the largest scales. This approach faces practical challenges. The angles in cosmic triangles deviate significantly from Euclidean expectations only if the triangles are very large, spanning a significant fraction of the observable universe. Measuring such vast triangles with sufficient precision is extremely difficult. Nevertheless, this method provides an elegant conceptual framework for understanding how cosmic geometry can be empirically tested. All these methods, from supernova observations to CMB analysis to gravitational lensing, point to the same conclusion. The universe appears remarkably flat, at least within our observable horizon. The curvature, if it exists at all, is too subtle to detect with current instruments. This convergence of evidence from multiple independent methods strengthens our confidence in the result. It's not just one technique or one dataset suggesting flatness, but a consilience of observations spanning different physical phenomena and cosmic epochs. Yet we must be careful about what this apparent flatness means. Our observations are limited to the observable universe, the region from which light has had time to reach us since the Big Bang. This observable universe is a sphere centered on Earth, with a radius of about 46.5 billion light-years, limited by the age of the universe and the finite speed of light. The entire universe might be much larger, perhaps infinitely so. The curvature we measure within our observable horizon might not represent the global curvature of the cosmos as a whole. It's possible that on even larger scales, beyond what we can see, the universe has curvature that we cannot detect locally. This distinction between local and global properties is familiar from everyday experience. Standing in a field, the Earth appears flat. Only by making careful measurements or climbing to a high vantage point do we recognize its curvature. Similarly, our entire observable universe might be such a small patch of a curved cosmos that the curvature is imperceptible to us. In mathematics, this concept is captured by the distinction between local and global geometry. A surface can be locally flat, meaning that small patches appear Euclidean, while having global curvature that becomes apparent only when we consider the entire surface. Our observable universe might be like a small, nearly flat patch on a vast curved space. This possibility relates to another fascinating concept in modern cosmology, the idea of cosmic variance. Because we can observe only one universe, and only a finite region of that universe, our measurements are subject to statistical uncertainty. We might happen to live in a region that is flatter or more curved than the cosmos as a whole. To account for this uncertainty, cosmologists must consider not just the measurements themselves, but the range of possible universes that could produce those measurements. This statistical approach recognizes the limitations of our cosmic perspective and the inherent uncertainties in inferring global properties from local observations. Despite these limitations, the evidence for a flat or nearly flat universe is compelling. The measurements from the Planck satellite, the most precise to date, constrain the curvature parameter to be within 0.003 of 0. This extraordinary flatness demands an explanation. The leading explanation comes from the theory of cosmic inflation, which proposes that the early universe underwent a brief period of exponential expansion within the first fraction of a second after the Big Bang. During this inflation, space stretched so dramatically that any initial curvature would have been flattened out, similar to how inflating a balloon smooths wrinkles on its surface. Imagine drawing a small circle on a deflated balloon. The circle is obviously curved, following the wrinkled surface, but as you inflate the balloon more and more, the circle appears increasingly flat from the perspective of a tiny observer on the balloon's surface. If the balloon were inflated to the size of the Earth, the original circle would appear perfectly flat to any local measurement. Similarly, inflation would have stretched the early universe so dramatically that any initial curvature would have been diluted beyond detection within our observable horizon. This naturally explains the flatness we observe, without requiring extraordinary fine-tuning of initial conditions. Inflation makes other predictions besides flatness, including the specific pattern of temperature fluctuations in the CMB and the nearly scale invariant spectrum of primordial density perturbations. The confirmation of these predictions by observations lends credibility to the inflationary paradigm and its explanation for cosmic flatness. Yet the question of whether the universe is precisely flat or merely very close to flat remains open. Current measurements are consistent with perfect flatness, but also allow for slight positive or negative curvature. Future observations, with more precise measurements of the CMB and large-scale structure, may be able to detect these subtle deviations from flatness if they exist. The implications of cosmic geometry extend beyond astronomy to fundamental questions about the nature of reality. If the universe is positively curved and finite, it contains a finite amount of matter and a finite number of possible particle configurations. Given enough time, patterns would necessarily repeat. In an eternal universe with positive curvature, history would eventually repeat itself. If the universe is flat or negatively curved and infinite, it contains an infinite amount of matter and an infinite number of possible configurations. In such a cosmos, every physically possible arrangement of particles would exist somewhere, including exact copies of Earth and its inhabitants. This mind-boggling implication of infinite space challenges our notions of uniqueness and identity. The geometry of space also influences how we understand the beginning and end of the universe. In the simplest models, a positively curved universe would eventually recollapse in a big crunch, the reverse of the Big Bang. A flat or negatively curved universe would expand forever. However, the discovery of dark energy complicates this picture, potentially allowing even positively curved universes to expand eternally. As we continue to measure the shape of the cosmos with increasing precision, we're not just mapping its geometry, but exploring its origin, evolution, and ultimate fate. We're testing theories of cosmic inflation and probing the nature of dark energy. We're constraining the amount of matter and energy in the universe and investigating how these components interact. This quest to determine the curvature of space represents one of humanity's greatest intellectual adventures. From our tiny planet, we've developed methods to measure the geometry of the entire observable universe. We've built instruments of extraordinary sensitivity, from ground-based telescopes to space observatories, to detect the subtle signatures of cosmic curvature. We've created mathematical frameworks that allow us to interpret these observations and test our theories against reality. The current evidence suggests a universe that is flat, or very nearly so, extending perhaps infinitely in all directions. Yet this evidence comes from a finite region, our observable horizon, leaving open the possibility of curvature on even larger scales. The complete shape of the cosmos might always remain partially hidden from us, accessible only through mathematical models and theoretical inference. Still, the progress we've made in measuring cosmic geometry represents a triumph of human curiosity and ingenuity. We've moved from myths and speculation to precise measurements and testable theories. We've developed a cosmic perspective that allows us to see our planet, our solar system, and even our galaxy as tiny parts of a vast and geometrically elegant whole. As we continue this journey of cosmic exploration, we're guided by the subtle clues left in the CMB, in the distribution of galaxies, and in the paths of light across billions of light years. These clues are like shadows cast by the shape of space itself, faint but discernible patterns that reveal the underlying geometry of everything. To measure something as vast as space, we measure the shadows it casts, in the pattern of ancient light, in the clustering of distant galaxies, in the bending of cosmic rays around massive structures, we find the imprint of geometry itself. Through these shadows, we glimpse the shape of reality, the form that contains all things, the answer to our question, is the universe flat? The whisper of the early universe tells us what shape we live in today. Imagine standing on a beach at dawn, watching the first light of a new day. The sun has not yet risen, but its glow already touches the sky, revealing what was hidden in darkness. In a similar way, cosmologists look to the first light of the universe, a faint glow that fills all of space, to reveal what would otherwise remain hidden, the shape of the cosmos itself. This ancient light is called the cosmic microwave background radiation, or CMB. It is the oldest light in the universe, released when the cosmos was just 380,000 years old, less than 0.1% of its current age. This primordial radiation has been traveling through space for nearly 14 billion years, carrying within it the imprint of the early universe and the geometry of space itself. The story of the CMB begins with the Big Bang. In its earliest moments, the universe was a hot, dense plasma, a soup of charged particles so energetic that atoms could not form. Light could not travel freely in this plasma. Photons would continually scatter off free electrons, making the early universe opaque, like a dense fog. As the universe expanded, it cooled. Eventually, about 380,000 years after the Big Bang, the temperature dropped enough for electrons and protons to combine, forming the first hydrogen atoms. This moment, called recombination, marked a profound transition. With electrons now bound to protons, photons could travel freely through space. The universe became transparent. The light released at this moment has been traveling ever since, stretched by the expansion of space from visible light to microwave radiation. This radiation surrounds us today, coming from all directions in the sky, a faint echo of the universe's fiery beginning. The CMB was discovered by accident in 1965. Two Bell Labs physicists, Arno Penzias and Robert Wilson, were testing a sensitive microwave antenna intended for communication satellite experiments. They detected a persistent background noise that seemed to come from all directions equally. At first, they thought the noise might be caused by pigeon droppings on the antenna or interference from nearby New York City. But after ruling out these and other potential sources, they realized they had stumbled upon something profound: the residual heat from the Big Bang itself. This discovery, which earned Penzias and Wilson the Nobel Prize in Physics, provided powerful evidence for the Big Bang theory and opened a new window on the early universe. The CMB showed that the cosmos began in a hot, dense state and has been expanding and cooling ever since, just as the Big Bang theory predicted. What makes the CMB particularly valuable for cosmology is its remarkable uniformity. The temperature of this radiation is almost exactly the same in all directions, about 2.7 Kelvin, just a few degrees above absolute zero. This uniformity tells us that the early universe was extraordinarily homogeneous, with matter and energy distributed evenly throughout space. But the CMB is not perfectly uniform. In 1992, the Cosmic Background Explorer satellite, or COBE, detected tiny variations in the CMB temperature, differences of only about 1 part in 100,000. These minute fluctuations are like cosmic fingerprints, revealing the seeds of all cosmic structure. The slightly denser regions in the early universe eventually grew into galaxies and galaxy clusters, while the slightly less dense regions evolved into the vast voids that separate these structures. The pattern of these temperature fluctuations across the sky contains a wealth of information about the universe, including its age, composition, and geometry. By carefully analyzing this pattern, scientists can determine whether space is flat, positively curved, or negatively curved. To understand how the CMB reveals cosmic geometry, imagine sound waves traveling through the early universe. Before recombination, the cosmos was filled with a hot plasma of charged particles. In this plasma, regions of slightly higher density would create pressure, pushing material outward. Gravity would pull this material back in, creating oscillations similar to sound waves in air. These acoustic oscillations had a characteristic size determined by the distance sound could travel in the early universe before recombination. This distance, called the sound horizon, serves as a standard ruler, a fixed scale imprinted in the pattern of CMB temperature fluctuations. Now, the apparent size of this ruler as we see it today depends on the geometry of space. If space is flat, following the rules of Euclidean geometry, the sound horizon will appear with a specific angular size on the sky. If space is positively curved like a sphere, the sound horizon will appear larger, as if seen through a magnifying glass. If space is negatively curved like a saddle, it will appear smaller. This relationship between geometry and apparent size allows scientists to determine the curvature of space by measuring the angular scale of fluctuations in the CMB. This measurement focuses on what cosmologists call the acoustic peaks in the CMB power spectrum, which represent the various harmonics of those primordial sound waves. The first and most prominent acoustic peak corresponds to sound waves that had just enough time to compress once before the universe became transparent. The position of this peak on the sky directly relates to the curvature of space. If the universe is flat, this peak should appear at an angular scale of about 1 degree. Several space missions have mapped the CMB with increasing precision to determine this critical measurement. The Cosmic Background Explorer provided the first evidence of the temperature fluctuations. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, mapped these fluctuations in much greater detail. And the Planck satellite, launched in 2009, created the most detailed map yet, measuring the CMB temperature across the entire sky with extraordinary accuracy. The results from these missions, particularly WMAP and Planck, indicate that our universe is remarkably close to flat. The first acoustic peak appears at almost exactly the position predicted for a flat universe. The curvature parameter, which measures the deviation from perfect flatness, is consistent with 0 to within a few tenths of a percent. This extraordinary flatness is one of the great puzzles of modern cosmology. In the standard Big Bang theory without inflation, the universe would need to have been fine-tuned to an incredible degree in its earliest moments to produce the flatness we observe today. This apparent coincidence has led many cosmologists to embrace the theory of cosmic inflation, which naturally explains why the universe appears flat. But the CMB reveals much more than just the geometry of space. It also tells us about the composition of the universe, the amounts of ordinary matter, dark matter, and dark energy. The relative heights of the different acoustic peaks in the CMB power spectrum depend on these cosmic ingredients, allowing scientists to measure their proportions with remarkable precision. These measurements indicate that ordinary matter, the stuff of atoms and molecules, makes up only about 5% of the cosmic energy budget. Dark matter, an invisible form of matter that interacts through gravity but not light, accounts for about 27%. And dark energy, a mysterious force driving the accelerated expansion of the universe, contributes the remaining 68%. This cosmic inventory, derived largely from the CMB, presents a humbling picture. The visible universe of stars and galaxies represents just a tiny fraction of what exists. The vast majority of the cosmos consists of dark components whose fundamental nature remains one of the great mysteries of modern physics. The CMB also provides our most precise measurement of the age of the universe. By analyzing the pattern of temperature fluctuations, cosmologists can determine how long the universe has been expanding since the Big Bang. The current best estimate is 13.8 billion years, with an uncertainty of less than 1%. Beyond these fundamental parameters, the CMB contains subtle signatures of the universe's earliest moments, potentially including the imprint of primordial gravitational waves generated during an inflationary epoch. These gravitational waves would leave a distinctive pattern in the polarization of the CMB, a particular twisting of the light's electric field as it travels through space. Several experiments, including the BICEP and Keck arrays at the South Pole, have searched for this polarization signature. A detection would provide strong evidence for inflation and allow scientists to probe the physics of the universe at energy scales far beyond what can be achieved in particle accelerators. So far, this signature has not been conclusively detected, and the search continues with increasingly sensitive instruments. The CMB also allows scientists to test for various exotic possibilities in cosmic geometry. One intriguing question is whether the universe might be finite yet unbounded, like the surface of a sphere but in higher dimensions. If space were to fold back on itself in this way, the CMB would show specific patterns of correlations across widely separated regions of the sky. Researchers have searched for these patterns, looking for what they call cosmic topology, the way space might connect to itself on the largest scales. These searches have not found conclusive evidence for such exotic topologies, suggesting that if the universe does fold back on itself, it does so on scales much larger than our observable horizon. Another fascinating aspect of the CMB is what it reveals about cosmic isotropy, whether the universe looks the same in all directions. The remarkable uniformity of the CMB temperature across the sky suggests that the universe is highly isotropic, with no preferred direction or axis. This isotropy is one of the foundational assumptions of modern cosmology, part of what scientists call the cosmological principle. The principle states that on the largest scales, the universe is both homogeneous, the same at every point, and isotropic, the same in every direction. The uniformity of the CMB provides strong empirical support for this principle. Yet there are intriguing hints of possible departures from perfect isotropy in the CMB. Researchers have identified several anomalies, patterns in the temperature fluctuations that seem slightly unusual compared to what standard cosmological models predict. These include the so-called cold spot, an unusually large cool region in the southern sky, and alignments of temperature patterns across large angular scales. These anomalies might be statistical flukes, the cosmic equivalent of seeing familiar shapes in clouds, or they might point to new physics beyond our current understanding, perhaps related to the universe's earliest moments or to large-scale cosmic structure. Ongoing research continues to investigate these puzzling features, searching for their origin and significance. The CMB not only reveals the past, but also helps us predict the future of the universe. The geometry of space, combined with the proportions of matter and energy, determines how the cosmos will evolve over trillions of years. The flatness of space, together with the dominance of dark energy indicated by the CMB, suggests that the universe will continue to expand at an accelerating rate forever. Galaxies beyond our local group will eventually recede so rapidly that they disappear from view, leaving future astronomers in our galaxy with an increasingly empty sky. This fate, known as the Big Freeze or cosmic heat death, represents a stark contrast to what earlier generations of cosmologists envisioned. Before the discovery of dark energy, many scientists thought that if the universe contained enough matter, its gravity would eventually halt and reverse the cosmic expansion, leading to a big crunch where everything collapsed back together. The CMB has helped reshape this vision of cosmic destiny, pointing toward an eternal expansion driven by dark energy. Yet we must remain humble about these predictions. The CMB reveals the universe as it was 13.8 billion years ago. What dark energy will do over trillions of years remains uncertain, and future observations may yet reveal surprises about the ultimate fate of the cosmos. As we reflect on what the CMB tells us about the shape of the universe, we should appreciate the extraordinary achievement it represents. From our tiny planet, we've developed instruments sensitive enough to detect temperature variations of a few millionths of a degree in radiation that has traveled across nearly 14 billion light-years. We've created mathematical models sophisticated enough to extract from these subtle variations the fundamental parameters of the cosmos, including its geometry, composition, and age. This achievement stands as one of humanity's greatest intellectual adventures, a testament to our curiosity about the universe and our ingenuity in exploring it. The CMB, this faint glow filling all of space, has become our most powerful tool for understanding the cosmos on its largest scales. Yet the CMB also reminds us of the limitations of our cosmic perspective. We can observe only the CMB from our location in space and time. We see only one realization of the quantum fluctuations that seeded cosmic structure. This limitation, what cosmologists call cosmic variance, places fundamental constraints on how precisely we can measure certain large-scale properties of the universe. Despite these limitations, the CMB has transformed our understanding of the cosmos. It has provided compelling evidence for the Big Bang theory while revealing the need for new physics, such as inflation and dark energy, to explain the universe we observe. It has shown us that space is remarkably flat, at least within our observable horizon, challenging us to explain this apparent fine-tuning. As we gaze at the CMB, we're looking at the surface of a sphere centered on our location, a sphere with a radius of nearly 14 billion light-years. This sphere represents the furthest we can directly see, the edge of our observable universe. Beyond lies more space, perhaps infinitely more, with its own galaxies and perhaps even its own observers, forever hidden from our view by the finite speed of light and the expansion of space. The flatness we observe within our cosmic horizon may or may not extend to these remote regions. The universe might curve on scales far larger than we can see, like the surface of the Earth that appears flat locally but reveals its curvature only when viewed from a greater distance. This possibility reminds us that the question, "Is the universe flat?" may have different answers depending on the scale we consider. Within our observable universe, the answer appears to be yes, remarkably so. But the universe as a whole might have a more complex geometry, perhaps varying from region to region, or curving gently on scales far beyond our cosmic horizon. The CMB, with its exquisite map of primordial sound waves frozen in the early universe, has brought us closer than ever to understanding our cosmic shape. It has shown us a universe that appears flat to the limits of our observation, a cosmos that began in a hot, dense state and has been expanding for nearly 14 billion years. This ancient light surrounds us, a constant reminder of our cosmic origins. Every cubic centimeter of space, including the space you occupy now, contains about 400 photons from the CMB, ancient light particles that have been traveling since the universe first became transparent. They pass through us continuously, silent messengers from the dawn of time. In their subtle patterns, these messengers carry information about the shape of the cosmos, the proportions of its contents, and the forces that govern its evolution. By listening to this whisper from the early universe, scientists have pieced together our most comprehensive picture yet of the geometry of everything. What emerges is an image of extraordinary elegance and simplicity, a universe that appears flat despite the complex interplay of forces that might have curved it, a cosmos whose expansion is accelerating due to a mysterious dark energy that makes up most of its content, a space-time that began in a singular moment and has been evolving ever since, following trajectories encoded in Einstein's equations of general relativity. The CMB, this ethereal glow that fills the entire sky, connecting us to our cosmic origins, has become our most powerful probe of this elegant universe. It anchors our understanding of cosmic history while pointing toward an eternal future of accelerated expansion. It reveals a cosmos poised with extraordinary precision at the boundary between different possible geometries. As technology advances, future experiments will map the CMB with even greater sensitivity, searching for fainter signals that might reveal new aspects of cosmic geometry. Space-based observatories and ground-based telescopes continue to refine our measurements, pushing the boundaries of what we can learn from this ancient light. Perhaps these future observations will confirm the perfect flatness suggested by current data, or perhaps they will detect subtle deviations from flatness, hints of curvature hidden just beyond the precision of our current instruments. Either way, the CMB will continue to guide our exploration of cosmic geometry, this whisper from the early universe teaching us about the shape we live in today. The whisper of the early universe tells us what shape we live in today, and what it tells us, with remarkable clarity and precision, is that we inhabit a cosmos that is flat, or very nearly so, extending perhaps infinitely in all directions, governed by elegant mathematical laws that allow for the emergence of structure, complexity, and ultimately, observers like ourselves who can decode the message written in this ancient light. We see what we can, but the edge of understanding always fades into the dark. The evidence seems compelling. Measurements of the cosmic microwave background, observations of distant supernovae, studies of the large-scale distribution of galaxies all point to the same conclusion: the universe is flat. The curvature parameter, which measures deviation from perfect flatness, is consistent with 0 to within a few tenths of a percent. If cosmic space is curved at all, the radius of curvature must be at least 250 times larger than the observable universe. This remarkable flatness represents one of the most precisely measured parameters in all of cosmology. It tells us that we live in a universe that follows Euclidean geometry on the largest scales, where parallel lines never meet. The angles of triangles sum to 180 degrees, and the shortest path between 2 points is a straight line. Yet despite the strength of this evidence, we must ask, is the case for cosmic flatness truly closed? Are there limitations to our measurements that might conceal subtle curvature? Could the universe be curved in ways we haven't yet detected, or on scales we cannot directly observe? The first limitation we must consider is the finite size of our cosmic horizon. The observable universe is not the universe in its entirety, but only the region from which light has had time to reach us since the Big Bang. This region forms a sphere centered on Earth with a radius of about 46 billion light-years, limited by the age of the universe and the finite speed of light. The entire universe might be much larger, perhaps infinitely so. The curvature we measure within our observable horizon might not represent the global curvature of the cosmos as a whole. It's possible that on even larger scales, beyond what we can see, the universe has curvature that we cannot detect locally. This distinction between local and global properties is familiar from everyday experience. Standing on a beach, the Earth appears flat. Only by making careful measurements or climbing to a high vantage point do we recognize its curvature. Similarly, our entire observable universe might be such a small patch of a curved cosmos that the curvature is imperceptible to us. In mathematics, this concept is captured by the distinction between local and global geometry. A surface can be locally flat, meaning that small patches appear Euclidean, while having global curvature that becomes apparent only when we consider the entire surface. Our observable universe might be like a small, nearly flat patch on a vast curved space. A related limitation is cosmic variance, the statistical uncertainty that arises because we can observe only one realization of the universe. The temperature fluctuations in the cosmic microwave background, which provide our best constraints on cosmic curvature, are the result of quantum processes in the early universe. If we could observe multiple universes or multiple widely separated regions of our own universe, we might see different patterns of fluctuations. This fundamental limitation means that even with perfect instruments, certain large-scale properties of the universe, including its curvature, can only be measured with finite precision. We might happen to live in a region that is flatter or more curved than the cosmos as a whole. Another consideration is the precision of our measurements. While current observations constrain the curvature parameter to be within a few tenths of a percent of zero, this still leaves room for slight curvature. A universe with positive curvature and a radius just a few times larger than our observable horizon would appear nearly flat to our instruments while still being finite and bounded. Such a universe would have profound implications. If cosmic space curves back on itself like a higher dimensional sphere, then traveling far enough in one direction would eventually bring you back to your starting point, having circumnavigated the entire cosmos. The universe would contain a finite amount of matter and a finite number of galaxies, despite having no edge or boundary. Conversely, a universe with slight negative curvature would be infinite and unbounded, extending forever in all directions. Such a cosmos would contain an infinite amount of matter and an infinite number of galaxies, with space becoming more stretched and hyperbolic at ever larger scales. Either possibility, slight positive or negative curvature, is consistent with current observations. The true geometry of the universe might lie just beyond the precision of our measurements, waiting to be revealed by more sensitive instruments or more sophisticated analysis. Even the interpretation of our measurements involves assumptions that could mask true cosmic curvature. When astronomers analyze the cosmic microwave background or the distribution of galaxies, they typically assume a particular model of the universe with specific properties and evolution. If the actual universe differs from these models in subtle ways, it could affect our inferences about its geometry. For example, most analyses assume that the dark energy driving cosmic acceleration has a constant density over time, corresponding to Einstein's cosmological constant. But if dark energy varies with time or space, it could mimic the effects of curvature or mask true curvature in our observations. Similarly, if the early universe underwent a more complex inflationary period than our standard models suggest, it could affect the patterns we see in the cosmic microwave background and our interpretation of those patterns in terms of cosmic geometry. These considerations don't invalidate the evidence for flatness, but remind us of the complexity of cosmological inference. We observe the universe through multiple filters, both instrumental and conceptual. Our conclusions about cosmic geometry depend not just on what we see, but on how we interpret what we see. Another fascinating possibility is that the universe might be flat, yet finite. In mathematics, certain topological spaces, such as the torus, can be locally flat everywhere while having a finite volume. Imagine a video game where leaving the right edge of the screen brings you back in from the left, and leaving the top brings you back in from the bottom. The game world is flat but finite, with no edge but a limited area. Our universe could have a similar topology, being flat in terms of its local geometry, but connected in ways that make it finite. If space were to fold back on itself like this, we might see repeated patterns in the cosmic microwave background or in the distribution of distant galaxies as light from the same objects reaches us from different directions. Astronomers have searched for these patterns, looking for what they call cosmic topology, the way space might connect to itself on the largest scales. These searches have not found conclusive evidence for such exotic topologies, suggesting that if the universe does fold back on itself, it does so on scales much larger than our observable horizon. Beyond these observational considerations, theoretical perspectives also complicate the question of cosmic flatness. The theory of cosmic inflation, which proposes that the universe underwent a period of exponential expansion in its earliest moments, naturally explains the flatness we observe. During inflation, space would have stretched so dramatically that any initial curvature would have been flattened out, similar to how inflating a balloon smooths wrinkles on its surface. A small, highly curved region of space would have been expanded to scales much larger than our observable universe, appearing flat to any local measurement. This inflationary explanation for flatness is compelling, especially since inflation also explains other observed features of the cosmos, such as its homogeneity and the specific pattern of fluctuations in the cosmic microwave background. But it raises a new question. If inflation made the observable universe so flat, is there significant curvature beyond our cosmic horizon, in regions that expanded from different parts of the pre-inflationary cosmos? Some versions of inflation theory, including eternal inflation, suggest that our observable universe is just one bubble in a vast multiverse, with different bubbles potentially having different properties, including different curvatures. In this picture, the flatness of our observable universe would be a local property, not representative of the multiverse as a whole. These speculative ideas remind us of the limitations of our cosmic perspective. We can directly observe only a tiny fraction of what may be an infinite cosmos. The true shape of the universe in its entirety might forever remain beyond our empirical reach, accessible only through mathematical models and theoretical inference. Yet even with these limitations, the evidence for a flat or nearly flat universe within our observable horizon is impressive. Multiple independent methods, using different physical phenomena and different observational techniques, all point to the same conclusion. This convergence of evidence strengthens our confidence in the result. The apparent flatness of the universe also has profound implications for its past and future. In the simplest cosmological models, a flat universe sits at the boundary between different possible fates. A universe with positive curvature contains enough matter for gravity to eventually halt and reverse the cosmic expansion, leading to a big crunch. A universe with negative curvature contains too little matter for this to happen, ensuring eternal expansion. A precisely flat universe represents a perfect balance, with just enough matter to slow the expansion asymptotically to zero after an infinite time. This critical density defines what cosmologists call the Einstein de Sitter model, once considered the most elegant possibility for our cosmos. However, the discovery of dark energy has changed this picture dramatically. Even a flat universe will expand forever if dark energy continues to drive cosmic acceleration. The geometry of space is no longer the sole determinant of the universe's fate. This changing understanding illustrates how our concept of cosmic flatness has evolved over time. When Einstein first applied his theory of general relativity to the universe as a whole, he assumed a static cosmos, neither expanding nor contracting. To achieve this, he added a term to his equations called the cosmological constant, a sort of anti-gravity that would counterbalance the attractive force of matter. But modern observations suggest that something very much like the cosmological constant does exist in the form of dark energy, driving an accelerating cosmic expansion. This accelerating expansion further complicates the relationship between geometry and destiny. In a universe dominated by dark energy, even positively curved space can expand forever, never recollapsing despite its finite volume. The ultimate fate of the cosmos depends not just on its shape, but on the nature of the mysterious dark energy that fills it. As we contemplate these cosmic possibilities, we should remember that our understanding continues to evolve. Future observations may detect subtle deviations from flatness that current instruments cannot resolve. Theoretical advances may suggest new ways to test cosmic geometry or new frameworks for interpreting existing observations. One promising direction involves gravitational waves, ripples in spacetime first detected in 2015. These waves travel across the universe carrying information about cataclysmic events such as the mergers of black holes. Because gravitational waves interact very weakly with matter, they can reach us from the earliest moments of cosmic history, potentially carrying imprints of the universe's shape. Another frontier involves mapping the distribution of matter with unprecedented precision. Next-generation surveys, such as those from the Vera Rubin Observatory and the Euclid Space Telescope, will create three-dimensional maps of billions of galaxies. These maps will reveal the large-scale structure of the universe in exquisite detail, allowing for new tests of cosmic geometry. Advances in cosmic microwave background observations also continue. Ground-based telescopes in Antarctica and Chile are measuring the polarization of the CMB with increasing sensitivity, searching for the imprint of primordial gravitational waves that could confirm the theory of inflation and provide new insights into the early universe. These ongoing and future observations may reveal subtle curvature hidden just beyond the precision of current measurements, or they may tighten the constraints further, showing that the universe is flat to even greater precision. Either outcome would deepen our understanding of cosmic geometry and its implications for the nature of reality. As we await these advances, we can reflect on what the apparent flatness of the universe tells us about our place in the cosmos. If space is truly flat and infinite, as current evidence suggests, then the observable universe, vast as it seems, represents an infinitesimal fraction of what exists. Beyond our cosmic horizon lie countless other galaxies, perhaps even other observers, contemplating their own cosmic horizons. In such an infinite cosmos, every physically possible arrangement of matter would exist, not just once, but infinitely many times. This mind-boggling implication challenges our notions of uniqueness and identity. If the universe is truly infinite, there are infinitely many planets identical to Earth, with beings identical to ourselves living out every possible variation of our lives. Even if the universe is only nearly flat, with a radius of curvature many times larger than our observable horizon, it would still be vast beyond comprehension. A positively curved universe, with a radius just 10 times larger than what we can see, would contain thousands of times more galaxies than are visible to us. These reflections on cosmic scales remind us of the limitations of human perception and understanding. We evolved to comprehend distances measured in meters and kilometers, not billions of light years. Our intuitions about space and shape emerge from our experience on the surface of the Earth, not from the cosmic geometry that current evidence suggests. Yet despite these limitations, we've developed mathematical frameworks and observational techniques that allow us to probe the shape of the entire observable universe. We've built instruments sensitive enough to detect temperature variations of a few millionths of a degree in ancient radiation. We've created models sophisticated enough to extract from these subtle variations the fundamental parameters of the cosmos. This achievement represents one of humanity's greatest intellectual adventures, a testament to our curiosity about the universe and our ingenuity in exploring it. From our tiny planet, we've determined that the universe is flat to within a few tenths of a percent, a measurement of astonishing precision given the vast scales involved. Yet we must remain humble about what we know and what remains unknown. The apparent flatness of the observable universe doesn't preclude curvature on even larger scales, beyond what we can directly see. The universe might have a complex geometry that appears flat within our limited perspective, just as the Earth appears flat to someone standing on its surface. As we continue to refine our measurements and expand our theoretical understanding, we move closer to answering the question that has guided our journey. Is the universe flat? Current evidence suggests that it is, at least within our observable horizon. But the complete answer might involve subtleties and complexities that we're only beginning to appreciate. The universe might be precisely flat, extending infinitely in all directions. Or it might have subtle curvature, positive or negative, that current instruments cannot detect. It might be flat, yet finite, with an exotic topology that connects distant regions of space. It might have varying curvature on scales beyond our cosmic horizon, in regions we can never directly observe. These possibilities remind us that our understanding of the cosmos remains incomplete. We see what we can with our instruments and our theories, but the edge of understanding always fades into the dark. Beyond lies more to discover, more to explore, more to understand about the shape of everything. In the earliest moments, the universe may have stretched itself into shape. The extraordinary flatness of the observable universe presents a profound puzzle. Why should space be so precisely balanced at the boundary between positive and negative curvature? It seems like an incredible coincidence, as if the universe were perched on the edge of a cosmic knife, neither falling one way nor the other for nearly 14 billion years. In the standard Big Bang theory, without additional elements, this flatness requires extreme fine-tuning of the initial conditions. The early universe would need to have had exactly the critical density, with a precision of 1 part in 10 to the power of 60 or more, to produce the flatness we observe today. Any slight deviation in those first moments would have been amplified over cosmic history, resulting in a universe either so positively curved that it would have recollapsed long ago, or so negatively curved that galaxies could never have formed. This fine-tuning problem, often called the flatness problem, is one of several puzzles that led cosmologists in the early 1980s to develop a new addition to the Big Bang theory, the theory of cosmic inflation. Inflation proposes that the very early universe, when it was less than a trillionth of a trillionth of a trillionth of a second old, underwent a brief period of exponential expansion, doubling in size perhaps 100 times or more in this fleeting moment. This inflationary epoch would have stretched space so dramatically that any initial curvature would have been flattened out, similar to how inflating a balloon smooths wrinkles on its surface. A small, highly curved region of space would have been expanded to scales much larger than our observable universe, appearing flat to any local measurement. To understand how inflation solves the flatness problem, imagine drawing a small circle on a deflated balloon. The circle is obviously curved, following the wrinkled surface. But as you inflate the balloon more and more, the circle appears increasingly flat from the perspective of a tiny observer on the balloon's surface. If the balloon were inflated to the size of the Earth, the original circle would appear perfectly flat to any local measurement. Similarly, inflation would have stretched the early universe so dramatically that any initial curvature would have been diluted beyond detection within our observable horizon. This naturally explains the flatness we observe without requiring extraordinary fine-tuning of initial conditions. The theory of inflation was first proposed by physicist Alan Guth in 1980, with significant developments by Andre Linde, Paul Steinhardt, and others in the following years. While initially motivated by the flatness problem and other puzzles like the horizon problem concerning the uniformity of the cosmic microwave background, inflation has become a cornerstone of modern cosmology, making specific predictions that have been confirmed by observations. But what could have caused such dramatic expansion in the universe's earliest moments? The answer lies in the behavior of quantum fields in extreme conditions. According to inflation theory, the very early universe was dominated by a quantum field, often called the inflaton field, in a high-energy state that acted like a kind of anti-gravity, driving exponential expansion. This state, known as a false vacuum, would have been metastable, meaning it was temporarily stable but ultimately decayed to a lower energy state. When this decay occurred, the tremendous energy of the inflaton field was released, filling the newly expanded space with a hot plasma of particles, setting the stage for the more familiar evolution of the Big Bang. The mathematics of inflation is rooted in Einstein's theory of general relativity, combined with quantum field theory. In general relativity, the curvature of space-time is determined by the energy content of the universe through Einstein's field equations. During inflation, the energy density of the inflaton field would have remained nearly constant as space expanded, creating a period of accelerated expansion. This accelerated expansion would have driven the universe toward flatness with extraordinary efficiency. Even if the universe began with significant curvature, positive or negative, inflation would have flattened it out so effectively that any remaining curvature within our observable horizon would be undetectably small. In fact, inflation predicts that the curvature parameter, omega, which measures the deviation from perfect flatness, should be precisely 1 to within 1 part in 100,000 or better. Current measurements, which find omega within a few tenths of a percent of 1, are consistent with this prediction. But inflation does more than just explain the flatness of the universe. It also makes other predictions that have been confirmed by observations. One of the most important is the pattern of density fluctuations that seeded cosmic structure. During inflation, quantum fluctuations in the inflaton field would have been stretched to macroscopic scales, creating slight variations in density across the expanding space. These tiny variations would become the seeds for all cosmic structure, the slightly denser regions eventually growing into galaxies and galaxy clusters through gravitational attraction. Inflation predicts that these density fluctuations should follow a nearly scale-invariant spectrum, meaning that fluctuations of different sizes have nearly the same amplitude. This prediction has been confirmed by observations of the cosmic microwave background, particularly by the WMAP and Planck satellites, which have mapped the temperature fluctuations in exquisite detail. These observations reveal a pattern remarkably consistent with inflationary predictions. The power spectrum of the CMB fluctuations shows a series of acoustic peaks with exactly the positions and relative heights expected from inflation, providing strong empirical support for the theory. Inflation also naturally explains the observed homogeneity and isotropy of the universe on large scales. Before inflation, regions now on opposite sides of the observable universe would have been in close contact, allowing them to establish thermal equilibrium. The subsequent inflationary expansion would have stretched these regions far apart, explaining why the cosmic microwave background has nearly the same temperature in all directions. Without inflation, this uniformity is puzzling because regions on opposite sides of the sky would never have been in causal contact, according to the standard Big Bang theory. Their similar temperatures would be an extraordinary coincidence, requiring precise fine-tuning of initial conditions. Inflation resolves this horizon problem by providing a mechanism for these distant regions to have once been close enough to equilibrate. Despite these successes, inflation remains a theory under development, with many variations and ongoing questions. One significant question concerns the nature of the inflaton field itself. While the mathematical description of this field is well established, its connection to particle physics and the fundamental forces remains uncertain. Various proposals link the inflaton to known or hypothetical particles and fields, including the Higgs field, axions, or fields associated with grand unified theories that describe the unification of fundamental forces at high energies. But the precise identity of the inflaton remains an open question in theoretical physics. Another area of active research involves the end of inflation, a period called reheating, when the energy of the inflaton field was converted into ordinary particles and radiation. This process, which connects the inflationary epoch to the standard Big Bang, involves complex interactions between quantum fields and remains incompletely understood. Perhaps the most exciting frontier in inflation research is the search for primordial gravitational waves. During inflation, quantum fluctuations would have created not only density variations, but also ripples in space-time itself, gravitational waves that would have been stretched by the cosmic expansion and should still be detectable today in the polarization of the cosmic microwave background. Several experiments, including the BICEP and Keck arrays at the South Pole and the Simons Observatory in Chile, are searching for this polarization signature known as B modes. A detection would provide strong evidence for inflation and allow scientists to determine the energy scale at which inflation occurred, a crucial parameter for theoretical models. Beyond these empirical tests, inflation has profound implications for our understanding of cosmic origins and perhaps even the multiverse. Some versions of inflation, particularly eternal inflation proposed by Andre Linde and others, suggest that inflation never ends completely. While it ended in our observable universe, allowing for the standard Big Bang evolution, it continues in other regions, constantly creating new, expanding bubbles of space-time. This scenario leads to the concept of a multiverse, where our observable universe is just one bubble in an endless sea of inflating space. Different bubbles might have different physical laws, different constants of nature, and different dimensionality, creating a vast cosmic diversity beyond our direct observation. In this multiverse picture, the apparent fine-tuning of our universe for the existence of life might be explained through a selection effect. Among the countless bubbles with different properties, we necessarily find ourselves in one compatible with our existence. This anthropic reasoning remains controversial, but has gained traction as a potential explanation for certain puzzling features of our universe, including the small but non-zero value of the cosmological constant. The connection between inflation and flatness takes on new meaning in this multiverse context. Instead of asking why the universe is flat, we might ask why we observe a flat universe. The answer would involve both the physical mechanism of inflation, which naturally produces locally flat regions, and the anthropic consideration that life might be more likely to evolve in regions with specific geometric properties. While these speculative ideas extend beyond current observational tests, they illustrate how the question of cosmic flatness connects to the deepest mysteries of physics and cosmology, from the quantum nature of space-time to the possibility of other universes beyond our own. Returning to more established science, let's consider in more detail how inflation makes the universe flat. Before inflation, space might have had significant curvature, either positive or negative. During inflation, space expanded exponentially, roughly doubling in size every 10 to the power of minus 35 seconds or less. This expansion would have occurred for only a tiny fraction of a second, perhaps 10 to the power of minus 30 seconds or even less, but the number of doublings would have been enormous, perhaps 100 or more. The result would be an expansion factor of at least 10 to the power of 30, stretching a region smaller than a proton to a size larger than the currently observable universe. Such dramatic stretching would flatten any initial curvature to undetectable levels. Mathematically, the curvature parameter omega approaches 1 exponentially during inflation. If inflation lasted long enough to solve the horizon problem, explaining the uniformity of the CMB, it would have driven omega so close to 1 that any deviation would be unmeasurable within our cosmic horizon. This prediction of precise flatness distinguishes inflation from other potential solutions to the cosmological puzzles. It's not just that inflation can accommodate flatness, it actively drives the universe toward flatness with extraordinary efficiency. The prediction of omega equals 1 is a key testable consequence of the theory. Current observations support this prediction, finding omega within a few tenths of a percent of 1. This remarkable agreement between theory and observation provides one of the strongest pieces of evidence for cosmic inflation. Yet we should note that inflation doesn't require the entire universe to be flat, only the region within our observable horizon and somewhat beyond. If the universe is vastly larger than what we can see, as inflation suggests, there could be regions with significant curvature far beyond our cosmic horizon. This raises an intriguing possibility. The universe as a whole might have complex topology and geometry, perhaps being finite yet unbounded like a higher dimensional torus, or having varying curvature from region to region. Within this diverse cosmic landscape, inflation would create locally flat regions like the one we inhabit. Such a scenario would reconcile the observed flatness of our visible universe with the possibility of a more complex global structure. It would mean that the question, is the universe flat, might have different answers depending on the scale we consider, similar to how the Earth appears flat locally but is globally spherical. The relationship between inflation and flatness also has implications for the fundamental nature of space itself. Is flatness a basic property of the universe, or is it something that emerged through physical processes like inflation? Does space have intrinsic geometry, or is geometry entirely determined by its contents through Einstein's equations of general relativity? In general relativity, the geometry of space-time and its material contents are intimately connected. Matter and energy curve space-time, and this curvature guides the motion of other matter and energy. During inflation, the energy of the inflaton field would have determined the curvature of space-time, driving it toward flatness through exponential expansion. This dynamic view of geometry differs from the older Newtonian concept of space as a fixed, absolute background against which physical processes unfold. In modern cosmology, the geometry of space itself evolves, shaped by the matter and energy it contains, and in turn influencing how that matter and energy behaves. Inflation represents a dramatic episode in this cosmic evolution, a period when the geometry of space was reshaped by the unique properties of the inflaton field. The flatness we observe today is a consequence of that reshaping, a geometric feature imprinted in the early universe and preserved through billions of years of subsequent expansion. This understanding of flatness as emergent rather than fundamental has philosophical implications. It suggests that the geometric properties of the universe are not arbitrary or preordained, but arise from specific physical processes operating under the laws of quantum mechanics and general relativity. The universe isn't flat by chance or design, but because inflation made it so. As we reflect on this inflationary explanation for cosmic flatness, we should appreciate the extraordinary achievement it represents. Without inflation, the flatness of the universe would be an inexplicable coincidence, requiring fine-tuning to 1 part in 10 to the power of 60 or more. With inflation, flatness becomes an expected outcome, a natural consequence of exponential expansion in the earliest moments of cosmic history. This transition from coincidence to explanation exemplifies the progress of science at its best. A puzzling observation, the flatness of the universe, motivated the development of a new theoretical framework, the theory of inflation. This theory not only explained the original puzzle, but made additional predictions that have been confirmed by subsequent observations, from the pattern of CMB fluctuations to the large-scale homogeneity of the cosmos. The success of inflation in explaining cosmic flatness and other features of the universe doesn't mean the theory is complete or without competitors. Alternative explanations for the same phenomena have been proposed, including bouncing cosmologies where our expanding universe emerged from the collapse of a previous cycle, or varying speed of light theories, where the apparent homogeneity of the universe results from a much faster propagation of light in the early cosmos. These alternative theories face their own challenges and have not achieved the same broad acceptance as inflation, but their continued development reminds us that science advances through the competition of ideas, with theories refined or replaced as new evidence emerges. For now, inflation provides our most compelling explanation for the flatness of the observable universe. It transforms an apparent coincidence into a necessary consequence of physical processes in the early cosmos. It connects the large-scale geometry we observe today to quantum fluctuations in the universe's earliest moments. It places the question of cosmic flatness within a broader framework that encompasses the origin of structure, the uniformity of the CMB, and potentially even the existence of a multiverse. As we continue to test the predictions of inflation with increasingly precise observations, we deepen our understanding of how the universe acquired its shape. We see more clearly the connection between the quantum realm of particles and fields and the cosmic realm of galaxies and geometry. We glimpse the processes that transformed a tiny, possibly curved region of space-time into the vast, flat cosmos we inhabit. In this way, the theory of inflation enriches our answer to the question that has guided our journey. Is the universe flat? Yes, current evidence suggests that it is, within our observable horizon, and inflation tells us why. The universe is flat because in its earliest moments it stretched itself into shape, transforming any initial curvature into the nearly perfect flatness we observe today. In the earliest moments, the universe may have stretched itself into shape, expanding exponentially to create the vast, flat cosmos we now call home. This elegant solution to the flatness problem exemplifies how modern cosmology explains the large-scale features of the universe through the physics of its smallest scales and earliest moments. Through inflation, the geometry of everything emerges from the quantum dance of fields in the newborn universe. The shape of space decides what happens next and what happens last. As we gaze at the night sky, watching stars that have shined for billions of years, a question inevitably arises. What is the ultimate destiny of this vast cosmos? Will the expansion that began with the Big Bang continue forever, or will it eventually reverse, bringing all matter back together in a cosmic finale? The answer, cosmologists have discovered, is intimately connected to the geometry of space itself. The shape of the universe influences not just its past, but its future as well. In the simplest cosmological models, before the discovery of dark energy, the fate of the universe was directly determined by its geometry. A positively curved universe, like the surface of a sphere, would contain enough matter for gravity to eventually halt and reverse the cosmic expansion. Such a universe would be finite yet boundless, expanding to a maximum size before contracting back into a fiery Big Crunch, perhaps to be reborn in a new cycle of expansion. A negatively curved universe, like a saddle surface, would contain too little matter to halt the expansion. It would grow forever, with galaxies moving apart at ever-increasing distances. The cosmos would become colder and more diffuse with time, eventually reaching a state where stars no longer form, and existing stars burn out one by one, leaving a dark, empty void. Between these two possibilities lies the flat universe, poised at the boundary between recollapse and eternal expansion. In a perfectly flat cosmos, the expansion would continue forever, but would asymptotically approach zero after an infinite time. Galaxies would move apart at an ever-slowing rate, like a ball thrown upward that never quite stops rising but climbs more and more slowly. This elegant relationship between geometry and destiny captivated cosmologists throughout much of the 20th century. The critical density that defines a flat universe became a key parameter in theoretical models, a cosmic balance point determining whether the universe would end in fire or ice. For decades, astronomers worked to measure the density of matter in the universe, counting galaxies, estimating their masses, and searching for the invisible dark matter that outweighs ordinary visible matter by a factor of roughly 5 to 1. The goal was to determine whether the total density exceeded, equaled, or fell short of the critical value, revealing the geometry and ultimate fate of the cosmos. The results of these measurements were puzzling. The density of matter, including both visible and dark components, appeared to be only about 30% of the critical value needed for a flat universe. This suggested a negatively curved cosmos that would expand forever, growing increasingly empty and cold. Yet other evidence, particularly from studies of the cosmic microwave background, indicated that the universe is remarkably flat. The acoustic peaks in the CMB power spectrum, which reveal the underlying geometry of space, matched the predictions for a flat universe with extraordinary precision. This apparent contradiction, too little matter for flatness, yet geometric evidence for flatness, hinted at a missing component in the cosmic inventory. Something else besides matter must be contributing to the energy density of the universe, bringing the total to exactly the critical value needed for flatness. The nature of this missing component was revealed in 1998, when two independent teams of astronomers made a shocking discovery. By carefully measuring the brightness of distant type Ia supernovae, stellar explosions that serve as cosmic standard candles, they found that the expansion of the universe is not slowing down as expected, but accelerating. Galaxies are moving apart at an ever-increasing rate, as if driven by a mysterious repulsive force. This discovery, which earned the 2011 Nobel Prize in Physics, introduced a new actor on the cosmic stage: dark energy. This enigmatic form of energy, which appears to be a property of space itself, exerts negative pressure that drives accelerated expansion. Dark energy accounts for about 68% of the mass energy content of the observable universe, with dark matter contributing about 27% and ordinary visible matter just 5%. When all these components are added together, ordinary matter, dark matter, and dark energy, the total comes remarkably close to the critical density needed for a flat universe. This cosmic coincidence, that we live precisely at the boundary between a positively and negatively curved universe, is one of the great mysteries of modern cosmology, potentially explained by inflation or other early universe processes. But the discovery of dark energy dramatically changed our understanding of the relationship between geometry and destiny. Even a flat or positively curved universe will expand forever if dark energy continues to drive cosmic acceleration. The geometry of space is no longer the sole determinant of the universe's fate. To understand this new cosmic paradigm, we must explore how dark energy affects the evolution of the universe. Unlike ordinary matter and energy, which become more diffuse as space expands, the density of dark energy appears to remain constant. Each cubic meter of new space created by expansion contains the same amount of dark energy as existing space. This constant energy density leads to ever-increasing acceleration. In a universe dominated by dark energy, as ours appears to be, the expansion will not only continue forever, but will accelerate without bound. Galaxies beyond our local group will eventually recede so rapidly that they disappear from view. their light stretched to undetectable wavelengths by the expanding space between us. After about 100 billion years, all galaxies outside our local group will become invisible, even with the most powerful telescopes imaginable. Future astronomers, if they exist, will see only a small collection of nearby galaxies surrounded by darkness, with no way to observe the vast cosmic web that we can still see today. This accelerated expansion will continue relentlessly. After trillions of years, even the local group of galaxies will be torn apart. Individual galaxies will remain bound by their own gravity, but the space between galaxies will stretch so rapidly that light can no longer bridge the gap. Within each isolated galaxy, stars will gradually burn out. The massive bright stars will exhaust their fuel first, followed by medium-sized stars like our Sun, and finally, the small, dim red dwarfs, which can shine for trillions of years. Eventually, all stars will exhaust their nuclear fuel, leaving behind white dwarfs, neutron stars, and black holes. These stellar remnants will slowly radiate away their remaining energy, cooling towards absolute zero. Over unimaginably vast timescales, quantum processes will cause protons to decay, disintegrating ordinary matter. Black holes will evaporate through Hawking radiation, releasing their energy back into the cosmos. After perhaps 10 to the power of 100 years, a time span so vast it dwarfs the current age of the universe by an almost inconceivable margin, even the largest black holes will have evaporated. The universe will consist only of scattered elementary particles and radiation, eternally expanding and eternally cooling toward absolute zero. This scenario, known as the Big Freeze or heat death of the universe, represents the current best guess for the ultimate fate of our cosmos. It's a stark contrast to the oscillating universe or the Big Crunch that cosmologists once envisioned as possible destinies for a curved universe. But this projection assumes that dark energy behaves as a cosmological constant, with unchanging density over time. If dark energy is not constant, but varies with time or space, the ultimate fate of the universe could be dramatically different. If dark energy weakens over time, the cosmic acceleration might eventually slow or even reverse, potentially allowing gravity to reassert its influence and bring about a big crunch after all. Given these uncertainties about the nature of dark energy, we cannot predict with absolute confidence the ultimate fate of the universe, even knowing its present geometry. The shape of space influences cosmic destiny, but does not uniquely determine it. Still, the current evidence strongly suggests a flat universe that will expand forever, growing increasingly empty and cold as dark energy drives an accelerating expansion. This fate, while bleak from a human perspective, has a certain austere beauty, a cosmos evolving from the hot, dense state of the Big Bang through the rich complexity of galaxies, stars, and life, and ultimately toward a quiet dissipation of all structure. But this picture of cosmic evolution raises profound questions about time and entropy. The second law of thermodynamics states that entropy, a measure of disorder, always increases in closed systems. As the universe expands and cools, it approaches a state of maximum entropy, where all energy is evenly distributed and no work can be performed. This inexorable increase in entropy defines what physicists call the arrow of time, the one-way direction from past to future that we experience in daily life. But if the universe began in a low entropy state at the Big Bang and will end in a high entropy state of heat death, why was the initial entropy so low? What set the arrow of time in the first place? This question, known as the problem of the past hypothesis, remains one of the deepest mysteries in physics and cosmology. It connects the geometry and fate of the universe to fundamental questions about the nature of time itself. One speculative answer involves the multiverse, the idea that our observable universe is just one bubble in a vast cosmic foam. Perhaps the arrow of time emerges from the particular conditions of our bubble, while other regions of the multiverse have different entropy gradients and different arrows of time. Another possibility involves quantum fluctuations in the far future. Even in a universe approaching heat death, random quantum processes could potentially create small regions of lower entropy, perhaps even nucleating new bubble universes through quantum tunneling. In this scenario, cosmic evolution would not end in eternal quiescence, but might seed new cycles of complexity. These speculative ideas remind us of the limitations of our current understanding. We can trace the evolution of the universe from the Big Bang to the present with remarkable precision, and we can project its future evolution based on current observations. But the ultimate beginning and end of the cosmos remain shrouded in mystery, touching on questions that may require physics beyond our current theories. What is clear is that the geometry of space plays a crucial role in this cosmic drama. The flatness we observe, likely resulting from inflation in the earliest moments after the Big Bang, sets the stage for the universe's evolution. It tells us that the total energy density of the cosmos precisely matches the critical value, a cosmic coincidence that has profound implications for the past and future of all things. In a flat universe, space-time has zero curvature on the largest scales, following the rules of Euclidean geometry. Parallel lines remain parallel forever, and the shortest distance between 2 points is a straight line. This geometry allows for a universe that is perfectly balanced between different possible fates, a cosmos poised on the edge of diverse destinies. Without dark energy, a flat universe would expand forever, but at an ever-slowing rate. The mutual gravitational attraction of all matter would gradually break the expansion, like a ball thrown upward that continues to rise but more and more slowly. After an infinite time, the expansion would approach but never quite reach zero. This model, known as the Einstein-de Sitter universe, was once considered the most elegant possibility for our cosmos. It represented a perfect balance, with just enough matter to ensure eternal expansion, but not enough for recollapse, a universe that dances forever on the boundary between different fates. The discovery of dark energy revealed that our universe, while apparently flat, does not follow this elegant trajectory. Instead, the cosmic expansion is accelerating, driven by the negative pressure of dark energy. The universe started with a rapid expansion in the Big Bang, slowed down as matter's gravitational influence dominated, and has now entered a new phase of accelerating expansion as dark energy takes over. This three-phase evolution, from rapid early expansion to deceleration to recent acceleration, emerges from the changing balance between different components of the cosmic energy budget. In the early universe, radiation dominated, creating a rapid expansion. As the universe cooled, matter became the main influence, slowing the expansion through gravitational attraction. In the recent cosmic past, about 5 billion years ago, dark energy became dominant, initiating the current accelerating phase. Throughout this complex history, the total energy density has remained at the critical value needed for flatness. This suggests that flatness is a fundamental feature of our universe, possibly established by inflation and preserved through billions of years of evolution. But flatness does not mean static or unchanging. A flat universe is dynamic, expanding according to the rules of general relativity, with its rate of expansion determined by the mix of matter, radiation, and dark energy it contains. Flatness describes the geometry of space on the largest scales, not the behavior of the universe over time. As we contemplate the fate of the universe, we should remember that our projections assume the continued validity of our current physical theories. General relativity and quantum mechanics, the twin pillars of modern physics, have been tested with extraordinary precision in many contexts, but they have not been tested over the vast timescales we're considering for cosmic evolution. It's possible that new physics, currently unknown to us, might alter the trajectory of the universe in the far future. Perhaps dark energy has quantum properties that will change its behavior. Perhaps gravity follows different rules at extremely low densities or over extremely large distances. Perhaps the vacuum itself is unstable, allowing for transitions to other states with different physical laws. These possibilities remind us that our understanding of cosmic destiny, like all scientific knowledge, is provisional and incomplete. We can make predictions based on our best current theories, but we must remain open to new discoveries that might change our perspective. For now, the evidence points to a flat universe that will expand forever, driven by the mysterious dark energy that makes up most of its content. This scenario, sometimes called the Big Freeze, envisions a cosmos growing increasingly vast, empty, and cold, with structure gradually dissolving into a diffuse soup of elementary particles and radiation. From a human perspective, this fate might seem bleak, but it's worth noting that the timescales involved are so vast as to be almost meaningless for human experience. Even the death of our sun, which will occur in about 5 billion years, lies so far in the future that human civilization, if it survives, will be unrecognizably different by then. The ultimate fate of the universe, trillions upon trillions of years hence, has little practical relevance for our species. What matters more is the remarkable fact that we can even contemplate these cosmic questions. We are tiny beings on a small planet, orbiting an ordinary star in one galaxy among billions. Yet through science and mathematics, we can trace the evolution of the entire observable universe from its fiery beginning to its cold, distant future. We can measure the curvature of space-time and calculate the density of dark energy. We can project the trajectory of cosmic expansion over timescales that dwarf human history. This cosmic perspective, this ability to see beyond our immediate surroundings to the largest scales of space and time, represents one of humanity's greatest intellectual achievements. It connects us to the universe in a profound way, showing us that we are not just in the cosmos but of it, our atoms forged in ancient stars, our very existence a product of cosmic evolution. As we reflect on the relationship between flatness and fate, we are reminded that geometry shapes destiny. The flatness of the universe, likely established in its earliest moments through inflation, sets constraints on its possible futures. Combined with the properties of dark energy, this geometry points toward eternal expansion, an endless cosmic journey from the hot density of the Big Bang toward the cold emptiness of the Big Freeze. Yet within this vast cosmic narrative, there is time and space for all the rich complexity we observe, from galaxies and stars to planets and living beings. The same laws that govern the evolution of the universe also allow for the emergence of structure, complexity, and ultimately consciousness that can contemplate these very laws. The shape of space decides what happens next and what happens last. It influences the trajectory of cosmic evolution from beginning to end. And in our flat universe, balanced perfectly at the critical density, that trajectory leads toward an ever-expanding, ever-cooling cosmos where structure gradually dissolves, but where the memory of a once vibrant universe remains encoded in the scattered radiation that fills all of space. Even in stillness, the flat universe buzzes with invisible life. The vast emptiness between galaxies seems utterly void, an absence rather than a presence. Yet modern physics tells us that this apparent nothingness is actually teeming with activity. Empty space is not empty at all, but filled with quantum fields that permeate the entire universe. These fields, invisible to our direct perception but fundamental to all existence, behave differently depending on the geometry of space-time. In our flat universe, quantum fields take on particular properties that shape everything from the behavior of elementary particles to the expansion of the cosmos itself. To understand the relationship between flat space and quantum fields, we must first grasp what these fields are. In quantum field theory, the cornerstone of modern particle physics, everything in the universe is understood as excitations of underlying fields that exist everywhere. The electron is not a discrete particle but a vibration in the electron field. The photon, the particle of light, is a wave in the electromagnetic field. Even the recently discovered Higgs boson is an excitation of the Higgs field that permeates all of space. These quantum fields exist even in the absence of particles. The so-called vacuum state, what we typically think of as empty space, is actually the lowest energy state of all these fields. But this vacuum is far from quiescent. According to the principles of quantum mechanics, specifically the Heisenberg uncertainty principle, fields constantly fluctuate even in their ground state. These vacuum fluctuations give rise to a seething quantum foam of virtual particles that pop in and out of existence too quickly to be directly observed. The behavior of these quantum fields and their vacuum fluctuations depends crucially on the geometry of space-time. In a flat universe, following the rules of Euclidean geometry, quantum fields spread out evenly in all directions. Their waves propagate according to straightforward mathematical relationships, and their energy states follow predictable patterns. This predictability in flat space makes our universe hospitable to the complex structures we observe. If space was significantly curved, quantum fields would behave differently. Their waves would focus or defocus, their energy states would shift, and the fundamental forces they mediate might have different strengths or ranges. One of the most profound connections between quantum fields and the geometry of space-time comes through the concept of vacuum energy. The quantum fluctuations in empty space contain energy, a seemingly small amount in any tiny region, but adding up to an enormous value when integrated over the entire universe. This vacuum energy, in principle, should contribute to the curvature of spacetime through Einstein's equations of general relativity. Theoretical calculations of this vacuum energy yield a value that's enormously larger than the observed value of dark energy, by a factor of as many as 120 orders of magnitude. This discrepancy, often called the cosmological constant problem, represents one of the greatest unsolved puzzles in theoretical physics. Why doesn't the vacuum energy of quantum fields curve spacetime far more dramatically than we observe? The fact that our universe appears flat, with any curvature from vacuum energy almost perfectly cancelled out, suggests either an extraordinary coincidence or some yet undiscovered mechanism that regulates the relationship between quantum fields and spacetime geometry. Various theoretical approaches, from supersymmetry to string theory to the anthropic principle within a multiverse framework, have been proposed to address this puzzle, but no consensus has emerged. Despite this theoretical challenge, the flat geometry of our universe provides an ideal setting for quantum fields to operate in ways that enable the physics we observe. The four fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, all propagate through quantum fields that extend throughout spacetime. In flat space, these forces follow inverse square laws, weakening with distance in predictable ways that allow for stable atoms, stars, and galaxies. The electromagnetic field, which mediates the force between charged particles, spreads through flat space according to Maxwell's equations. These elegant mathematical relationships, which unify electricity and magnetism, take their simplest form in flat spacetime. The resulting behavior of electromagnetic waves, including visible light, radio waves, and X-rays, enables everything from star formation to photosynthesis to human vision and technology. Similarly, the strong nuclear force, responsible for binding protons and neutrons in atomic nuclei, operates through the gluon field that permeates space. In flat spacetime, this force has precisely the right strength and range to create stable nuclei that can form the elements of the periodic table. If space were curved differently, the strong force might be too weak to bind nuclei, or too strong to allow the nuclear reactions that power stars. The weak nuclear force, which enables certain types of radioactive decay and is crucial for stellar nucleosynthesis, also depends on the flat geometry of spacetime for its particular characteristics. This force, mediated by the W and Z boson fields, allows stars to convert hydrogen into helium and eventually into heavier elements, creating the chemical diversity necessary for planets and life. Gravity, while described classically by Einstein's general relativity as the curvature of spacetime itself, is also thought to have a quantum description involving a graviton field. Though a complete quantum theory of gravity remains elusive, the behavior of gravity in our flat universe allows for the formation of cosmic structure on all scales, from galaxy clusters to planetary systems. Perhaps the most remarkable connection between flat space and quantum fields comes through the Higgs field, discovered in 2012 through the detection of its corresponding particle, the Higgs boson. This field pervades all of space and gives mass to elementary particles through their interactions with it. In the hot, dense, early universe, the Higgs field had different properties than it does today, and as the universe cooled and expanded, it underwent a phase transition, settling into its current state. This transition, known as electroweak symmetry breaking, was crucial for the formation of atoms and molecules, as it allowed electrons and quarks to have the specific masses they possess. In a universe with different geometry, this process might have unfolded differently, potentially creating particles with different masses and altering the entire course of cosmic chemical evolution. Beyond these established fields, various theoretical extensions to the standard model of particle physics propose additional fields that might permeate spacetime. These include fields associated with dark matter, dark energy, inflation, and other phenomena not yet fully understood. The behavior of these hypothetical fields would also be influenced by the flat geometry of our universe. One intriguing possibility is that dark energy itself, the mysterious force driving the accelerated expansion of the universe, might be a quantum field in a particular state. Unlike ordinary matter and radiation, which become more diffuse as space expands, the energy density of this field would remain constant, creating the accelerating expansion we observe. This field, sometimes called quintessence if it varies over time or space, would contribute exactly the right amount of energy to maintain the flatness of the universe. Combined with ordinary matter and dark matter, it would bring the total energy density to precisely the critical value needed for flat cosmic geometry. The coincidence that these different components add up to exactly the critical density represents one of the great puzzles of modern cosmology. It suggests either extraordinary fine-tuning of initial conditions, a new physical principle that enforces flatness, or the action of cosmic inflation that would have flattened the universe in its earliest moments, as we explored in a previous chapter. The relationship between quantum fields and flat space extends beyond the present to the early universe. During the inflationary epoch, that likely occurred in the first fraction of a second after the Big Bang, quantum fluctuations in the inflaton field, stretched to macroscopic scales by exponential expansion, became the seeds for all cosmic structure. These tiny quantum ripples in the primordial fields evolved into the slight density variations observed in the cosmic microwave background, which in turn grew through gravitational attraction into the galaxies and galaxy clusters we see today. The specific pattern of these fluctuations, nearly scale invariant with slightly more power at larger scales, is consistent with quantum processes operating in an exponentially expanding flat spacetime. Even more remarkably, quantum fluctuations during inflation might have created ripples in spacetime itself, primordial gravitational waves that could still be detectable today in the polarization of the cosmic microwave background. Several experiments are searching for this signal, which would provide strong evidence for inflation and allow scientists to probe the quantum nature of gravity. The quantum nature of fields in flat space also manifests in the famous Casimir effect, first predicted by Dutch physicist Hendrik Casimir in 1948. When two uncharged metallic plates are placed very close together in a vacuum, they experience a small attractive force. This force arises because the tiny gap between the plates only allows certain wavelengths of vacuum fluctuations, while the space outside the plates permits all wavelengths. This difference in quantum field modes creates a pressure that pushes the plates together. The Casimir effect, confirmed experimentally, provides direct evidence for the reality of quantum vacuum fluctuations and demonstrates how boundary conditions can influence the behavior of fields in space. In a curved universe, the mathematics of this effect would be more complex, potentially altering the strength and nature of the force. Another fascinating aspect of quantum fields in flat space involves quantum entanglement, the mysterious connection between particles that allows them to remain correlated even when separated by vast distances. This phenomenon, which Einstein famously called spooky action at a distance, is a fundamental feature of quantum mechanics and has been confirmed by numerous experiments. Entanglement spreads through quantum fields in ways that depend on the geometry of space-time. In flat space, entangled particles maintain their correlations according to specific mathematical relationships that have been verified to high precision. These correlations appear to propagate instantaneously, though no information can actually travel faster than light. The flat geometry of our universe allows quantum entanglement to operate in the way our theories predict and our experiments confirm. If space were curved differently, the propagation of entanglement might follow different rules, potentially altering quantum information processes that may be fundamental to the fabric of reality itself. Beyond these physical implications, the relationship between quantum fields and flat space raises profound philosophical questions. If empty space is actually filled with quantum fields in constant fluctuation, what does this mean for our concepts of nothingness and existence? If virtual particles continuously pop in and out of the vacuum, where is the boundary between being and non-being? These questions touch on ancient philosophical debates about the nature of void and plenum, emptiness and form. Modern physics suggests a view more aligned with Eastern philosophical traditions, where emptiness is not an absence, but a dynamic fullness, teeming with potential. The quantum vacuum, far from being nothing, contains within it the seeds of everything. This perspective finds mathematical expression in the concept of symmetry breaking in quantum field theory. Many physical systems have underlying symmetries that become hidden or broken under certain conditions. The vacuum state of a quantum field may have less symmetry than the equations that describe the field, leading to phenomena like the Higgs mechanism that gives particles mass. In the hot, dense early universe, these symmetries were more manifest, and the distinctions between different forces and particles were blurred. As the universe expanded and cooled, symmetries broke in sequence, like water freezing into ice, with a particular crystalline structure that hides the rotational symmetry of the liquid state. The flat geometry of our universe provides the canvas on which these symmetry-breaking processes unfolded, leading to the rich complexity we observe today. If space had different curvature, these processes might have occurred differently, potentially creating a universe with different forces, different particles, and different possibilities for structure and life. As we contemplate the relationship between flat space and quantum fields, we should remember that our understanding remains incomplete. The most fundamental questions, such as the unification of general relativity and quantum mechanics into a theory of quantum gravity, or the true nature of dark energy, have not been fully resolved. Various approaches, including string theory, loop quantum gravity, and causal set theory, seek to describe how spacetime itself might emerge from more fundamental quantum processes. In these frameworks, what we perceive as flat space might be an emergent property arising from interactions of more basic quantum entities, strings, loops, or discrete causal elements. The holographic principle, inspired by the physics of black holes, suggests that all the information contained in a volume of space can be encoded on its boundary surface. This radical idea, if correct, would mean that our three-dimensional reality with its quantum fields might be a projection of processes occurring on a distant two-dimensional surface, similar to how a hologram creates the illusion of depth from a flat image. These speculative ideas push the boundaries of current physics and mathematics, reminding us that our understanding of quantum fields in flat space may be just an approximation of a deeper reality. Future discoveries might reveal new layers of structure beneath what we currently perceive as empty space, just as quantum mechanics revealed the teeming activity beneath the apparently smooth classical fields of 19th century physics. For now, the evidence suggests that we live in a remarkably flat universe permeated by quantum fields whose behavior enables the rich complexity we observe. These fields, through their particles and interactions, create atoms, molecules, stars, and galaxies. Through their vacuum energy, they may drive the acceleration of cosmic expansion. Through their fluctuations during inflation, they seeded the structure of the entire observable universe. The flatness of space provides the ideal geometric environment for these quantum processes to unfold in ways that create a universe hospitable to complexity and life. The precise balance of forces, the stability of matter, and the predictable propagation of light all depend on the Euclidean geometry of flat spacetime. As we go about our daily lives, surrounded by seemingly solid objects in apparently empty space, we might pause to consider the extraordinary reality revealed by modern physics. The chair you sit on, the air you breathe, and the apparent emptiness between galaxies are all manifestations of quantum fields vibrating in flat spacetime. The vacuum itself is a dynamic entity, seething with virtual particles and storing enormous energy in its fluctuations. Even in stillness, the flat universe buzzes with invisible life. Quantum fields permeate every cubic centimeter of space, their vibrations creating the particles and forces that constitute all physical reality. In the seemingly empty void between stars, virtual pairs of particles and antiparticles continuously emerge and annihilate, their fleeting existence constrained by the uncertainty principle. This quantum activity in flat space underlies everything we experience, from the stability of matter to the passage of time, from the warmth of sunlight to the complexity of life. It reminds us that nothingness is not nothing, that emptiness is full of possibility, and that our flat universe, far from being a featureless void, is a vibrant, dynamic tapestry of interacting fields that give rise to all the beauty and complexity we observe. What we call flat may be what we were shaped to see. As we gaze out at the stars, pondering the geometry of the cosmos, a curious question arises. How do we, tiny beings on a small planet, perceive the vast curvature of the universe? Our eyes and brains evolved to navigate a world of medium-sized objects moving at slow speeds. Our intuitive understanding of space and shape emerges from our experience on Earth, a local environment that appears flat on human scales, despite the planet's global curvature. Perhaps our perception of cosmic flatness tells us as much about ourselves as it does about the universe. The human visual system evolved to help our ancestors survive in the African savanna, not to comprehend the geometry of space-time. Our eyes capture two-dimensional projections of the world around us. Our brain reconstructs these flat images into a three-dimensional model, inferring depth from subtle cues like parallax, perspective, and the relative sizes of familiar objects. This neural processing happens so quickly and seamlessly that we're rarely aware of it. We simply see a world of objects in space, not the complex calculations our brain performs to create this perception. This perceptual machinery is exquisitely adapted to the scales and speeds of everyday life, where space appears to follow the rules of Euclidean geometry. Parallel lines, like railroad tracks, seem to converge in the distance, but we understand that this is an illusion of perspective, not true convergence. The angles of triangles sum to 180 degrees, as you can verify with any ruler and protractor. Light travels in what appear to be perfectly straight lines, bouncing off mirrors at predictable angles. Our perception of flatness is so ingrained that it took thousands of years of civilization before mathematicians like Nikolai Lobachevsky, Bernhard Riemann, and Janos Bolyai even began to explore the possibility of non-Euclidean geometries, mathematical systems where parallel lines might converge or diverge, and the angles of triangles might not sum to 180 degrees. These ideas, developed in the 19th century, initially seemed like abstract mathematical curiosities with no connection to physical reality. Only with Einstein's theory of general relativity, published in 1915, did physicists recognize that the geometry of space itself might be curved by the presence of matter and energy. This revolutionary insight reframed gravity not as a force acting across distances, but as a curvature of spacetime that determines how objects move. The straight-line paths of planets around the Sun are actually geodesics, the shortest paths through curved spacetime, like great circles on the surface of a sphere. Yet this curved spacetime remains largely invisible to our direct perception. We don't see or feel the warping of space around massive objects like the Earth or the Sun. We experience its effects as what we call gravity, the familiar force that keeps our feet on the ground and planets in their orbits. Only through careful measurements and mathematical analysis do we detect the true geometry of space-time. This disconnect between our perception and cosmic reality highlights the limitations of human intuition. We evolved on a planet where local space appears flat, where the curvature of Earth only becomes apparent at scales much larger than our bodies. A person standing in a field perceives a flat surface extending to the horizon. Only by climbing a mountain, sailing beyond the horizon, or observing the Earth from space do we recognize its spherical shape. Similarly, the curvature of the universe, if it exists at all, manifests at scales far beyond our direct experience. Our observable universe extends about 46 billion light-years in all directions, a distance so vast that it defies intuitive comprehension. If cosmic space has curvature, its radius would be at least 200 times larger than this already enormous span, based on current measurements. Such scales lie so far beyond human experience that we have no perceptual machinery to grasp them directly. Instead, we rely on instruments and mathematics to extend our senses beyond their natural limits. Radio telescopes detect cosmic microwave background radiation, invisible to our eyes. Satellite observatories measure the tiny temperature variations in this ancient light, with sensitivities far beyond human perception. Computer algorithms analyze these measurements, searching for patterns that might reveal the geometry of the cosmos. Through these technological extensions of our senses, we've determined that the universe appears remarkably flat, at least within our observable horizon. But this flatness, revealed by our instruments, may still be filtered through the lens of human perception and cognition. Our very concept of flatness is shaped by our embodied experience on Earth. We call surfaces flat when they don't curve significantly at the scales relevant to our bodies and actions. A table is flat enough to place objects on without them rolling off. A field is flat enough to run across without stumbling. The ocean appears flat to the horizon, though we know intellectually that it curves with the Earth's surface. This pragmatic, scale-dependent concept of flatness influences how we think about cosmic geometry. We describe the universe as flat because, within our observable horizon, it follows the rules of Euclidean geometry with extraordinary precision. Parallel light beams remain parallel, and cosmic triangles have angles summing to 180 degrees as far as we can measure. But this apparent flatness might be like the apparent flatness of the Earth's surface to a person standing in a field. From our limited vantage point, we cannot see the full extent of the cosmos. The universe might have curvature on scales beyond our observable horizon, curves too subtle or too vast for our current instruments to detect. This possibility highlights the relationship between perception and scale. Different geometrical properties become relevant at different scales. At the quantum scale, space-time might not be continuous at all, but granular or foamy, with fluctuations in the fabric of reality itself. At human scales, local space appears flat, following Euclidean rules. At planetary scales, we recognize spherical geometry, with great circles forming the shortest paths on the Earth's surface. At cosmic scales, the universe appears flat again, but might have curvature beyond what we can currently observe. Our perception of reality at each of these scales is shaped by the tools and conceptual frameworks we use to investigate it. Quantum physics reveals a probabilistic, wave-like reality at the smallest scales. Newtonian physics adequately describes the motion of medium-sized objects at modest speeds. General relativity unveils the curved space-time of massive objects and cosmic expansion. Each of these frameworks is valid within its domain of applicability, each revealing a different aspect of the underlying reality. The apparent flatness of the universe might reflect not just an objective feature of cosmic geometry, but also the particular way we've carved up reality with our theoretical models. Different mathematical frameworks might reveal different aspects of the cosmos, just as different types of maps highlight different features of the Earth's surface. This interplay between perception, cognition, and reality has deep philosophical implications. The German philosopher Immanuel Kant argued that space and time are not features of external reality, but forms of intuition imposed by the human mind. We perceive objects as existing in space and events as occurring in time, because that's how our cognitive apparatus structures experience, not necessarily because space and time exist independently of perception. Modern neuroscience has shown that our experience of space is indeed constructed by the brain, not simply given in perception. Various regions of the cerebral cortex process spatial information, creating our sense of depth, distance, and three-dimensional structure. People with damage to these brain areas can lose the ability to perceive spatial relationships, even though their eyes still function normally. This constructed nature of spatial perception doesn't mean that external reality is an illusion, or that the geometry of the universe is merely a figment of imagination. Rather, it suggests that our understanding of cosmic shapes is mediated by our perceptual and cognitive systems, which evolved for very different purposes than contemplating the curvature of spacetime. The apparent flatness of the universe, revealed through our instruments and mathematical models, represents a remarkable convergence of human understanding and cosmic structure. We've developed tools and concepts that allow us to probe the geometry of reality far beyond the scales our ancestors could perceive or even imagine. Yet these tools and concepts are themselves products of human minds, shaped by evolution and culture. This reciprocal relationship between perception and reality extends to our understanding of science itself. When we ask whether the universe is flat, we're not just interrogating external reality, but also examining the frameworks we use to make sense of that reality. The question involves both objective features of the cosmos and subjective aspects of human cognition. Perhaps the most profound implication of this perspective is that our understanding of cosmic geometry is not a discovery of some pre-existing truth, but a co-creation involving both the structure of the universe and the structure of human cognition. The flatness we perceive emerges from the interaction between reality and our methods of investigating it. This doesn't mean that the geometry of the universe is arbitrary, or that all possible descriptions are equally valid. Some models match observations better than others, allowing more accurate predictions about cosmic evolution and structure. The evidence strongly suggests that the observable universe is indeed remarkably close to flat, regardless of how we might perceive or conceptualize it. But this flatness, like all scientific knowledge, remains provisional and scale-dependent. It represents our best current understanding, subject to revision as we develop more sensitive instruments and more sophisticated theories. Future observations might reveal subtle curvature or exotic topological features currently beyond our detection. Future theoretical frameworks might reframe our entire understanding of what cosmic geometry means. The relationship between perception and reality becomes even more complex when we consider observers in different parts of the universe. Each observer has their own cosmic horizon, the spherical boundary beyond which light has not had time to reach them since the Big Bang. If space has curvature too subtle to detect within one observer's horizon, observers in widely separated regions might reach different conclusions about cosmic geometry based on their local measurements. This perspective from cosmic democracy, where no observer's vantage point is privileged, aligns with the cosmological principle, the assumption that the universe is homogeneous and isotropic on the largest scales. If this principle holds, all observers in similar cosmic environments should eventually converge on the same understanding of cosmic geometry, given sufficient observational precision. But the cosmological principle itself represents a human conceptual framework, a simplifying assumption that makes the mathematics of cosmology tractable. The actual universe might be more complex, with variations in density, curvature, or even fundamental constants across scales larger than any single observable horizon. These possibilities remind us of the limitations of human perception and understanding, even when extended by our most sophisticated instruments and theories. We see what we're equipped to see, conceptualize what our frameworks allow us to conceptualize. The flatness of the universe, while supported by strong evidence, remains influenced by how we observe and interpret the cosmos. This relationship between perception and reality extends to our everyday experience as well. When we look at the night sky, we don't see the true structure of the cosmos, but a two-dimensional projection of stars and galaxies at vastly different distances. Our brain creates a sense of depth and scale, but this mental model differs significantly from the actual distribution of cosmic objects. Similarly, we perceive stars as points of light, not as the enormous thermonuclear furnaces they actually are. We see the sun move across the sky, not the Earth rotating on its axis. We experience solid objects as continuous and static, not as collections of atoms in constant vibration. Our perception filters and transforms reality in countless ways, creating an experience adapted to our biological needs rather than a perfect representation of the external world. This doesn't mean our perception is illusory or that scientific understanding is impossible. Rather, it suggests that all knowledge involves an interaction between reality and the methods we use to investigate it. Science extends our perception beyond its natural limits through instruments and mathematics, creating increasingly accurate models of reality while acknowledging their provisional nature. The flatness of the universe, measured with extraordinary precision through cosmic microwave background observations, represents one of our most successful extensions of human perception. It tells us that space, on the largest observable scales, follows Euclidean geometry with remarkable accuracy. This knowledge, achieved through centuries of scientific development, allows us to project the universe's evolution from its fiery beginning to its cold, distant future. Yet this understanding remains shaped by the particular way humans perceive and conceptualize space. Our intuitive notions of flatness, derived from our experience on Earth's surface, influence how we frame cosmic questions and interpret observations. Different cognitive systems, evolved under different conditions, might conceptualize cosmic geometry in ways we cannot imagine. This perspective invites humility about our cosmic understanding. The apparent flatness of the universe represents both an objective feature of reality, supported by multiple independent lines of evidence, and a product of human perception and cognition, filtered through our particular evolutionary and cultural history. As we contemplate the shape of the cosmos, we're also contemplating the shape of human understanding itself, the ways our minds grasp and represent reality at scales far beyond our direct experience. The universe we perceive is both the universe that exists independently of us and the universe we're equipped to see. In an important sense, the cosmos we study is not just the external reality of stars and galaxies, dark matter and dark energy, but also the reality we construct through observation, measurement, mathematics, and theory. The flat universe revealed by our instruments is the universe as human science can currently perceive it, a remarkable achievement of intellect, yet still influenced by the particular way we, as a species, engage with reality. This doesn't diminish the significance of cosmic flatness, but enriches it, connecting this profound feature of the universe to the equally profound capacity of human minds to extend beyond their natural perceptual limits. Through science, we transcend the local and immediate, grasping structures and relationships on scales our ancestors could not even imagine. What we call flat may be what we were shaped to see, but in developing the tools and concepts of modern cosmology, we've shaped ourselves to see far beyond our natural limits, perceiving the geometry of the entire observable universe with astonishing precision. This reciprocal relationship between perception and reality, mind and cosmos, represents one of the most remarkable aspects of human existence, a kind of cosmic consciousness emerging from the very universe it seeks to understand. Flat doesn't always mean forever. It could mean connected. When we think of a flat universe, we often imagine an infinite expanse stretching endlessly in all directions, following the familiar rules of Euclidean geometry we learned in school. In such a cosmos, parallel lines never meet, the angles of triangles sum to exactly 180 degrees, and space extends without limit. But a remarkable possibility exists that challenges this intuitive picture. Could the universe be both flat and finite? Could space have no boundary or edge, yet contain a finite volume, like a video game, where leaving one side of the screen brings you back in from the opposite side? This seemingly paradoxical possibility emerges from the mathematics of topology, the branch of geometry concerned with properties that remain unchanged under continuous deformations, like stretching and bending. Topology distinguishes between the local geometry of space, whether it's flat or curved at each point, and its global connectivity, how different regions link together to form the complete shape. The simplest example of a space that is locally flat yet globally finite is the surface of a torus, the mathematical term for a donut shape. While a torus curves in 3 dimensions, an ant walking on its surface would experience locally flat geometry. Using a tiny protractor, the ant would find that triangles have angles summing to 180 degrees, yet this flat surface is finite in area and has no boundary. We can extend this concept to 3 dimensions, imagining a universe with the topology of a 3-dimensional torus. Such a universe would appear flat everywhere, with light traveling in straight lines and parallel beams never converging or diverging. Yet space would be finite in volume, with no boundary or edge. If you traveled far enough in any direction, you would eventually return to your starting point, having circumnavigated the entire cosmos. This toroidal universe is just one example of what mathematicians call multi-connected spaces. These are spaces where different regions connect in ways that create shortcuts or loops through the cosmos. Other possibilities include the 3-dimensional Klein bottle, the projective space, and various other exotic topologies allowed by mathematics. How might such a strange cosmic architecture arise? One possibility involves the very early universe, when space-time might have had quantum properties quite different from our current classical understanding. During this primordial epoch, the topology of space could have become fixed, like a phase transition in matter that determines its crystalline structure. Once established, this topology would persist through the subsequent expansion, creating the large-scale structure we might detect today. Evidence for such a multi-connected universe could potentially be found in the cosmic microwave background radiation, the ancient light released when the universe first became transparent about 380,000 years after the Big Bang. If space loops back on itself, we might observe matching patterns on opposite sides of the sky, as we would be seeing the same region from different directions. Astronomers have searched for these matched circles or other topological signatures in the CMB data from satellites like WMAP and Planck. So far, they have found no conclusive evidence for a multi-connected topology. suggesting that if the universe does loop back on itself, it does so on scales larger than our observable horizon. The current observational constraints indicate that if the universe is a three-dimensional torus, each dimension must be at least twice the diameter of the observable universe. If the universe is smaller than this, we would have detected the repetition of patterns in the cosmic microwave background. Despite these constraints, the possibility of a flat yet finite universe remains open, particularly on scales just beyond our current observational reach. Such a universe would have profound implications for our understanding of cosmic evolution and the ultimate fate of all things. In a finite universe, even if flat, the total amount of matter and energy would be finite. The number of atoms, stars, and galaxies would be large but limited. In contrast, a truly infinite universe would contain an infinite amount of matter arranged in every possible configuration, including exact copies of Earth and its inhabitants, occurring infinitely many times throughout the endless cosmos. This distinction between finite and infinite has philosophical as well as physical significance. An infinite universe raises questions about uniqueness and identity. If exact copies of you exist elsewhere, reading these same words and thinking these same thoughts, what does that mean for the concept of individual existence? A finite universe, even without boundaries, avoids these metaphysical complications while still potentially extending far beyond our observable horizon. A flat, yet finite universe also has implications for the long-term evolution of the cosmos. In an infinite flat universe with dark energy, galaxies would continue to move apart forever, with the space between them expanding at an accelerating rate. Eventually, each galaxy or local group of galaxies would become an island, unable to observe or interact with the rest of the universe. In a finite, flat universe, the dynamics would be similar within each local region, but the finite volume would impose certain constraints. Depending on the specific topology, light might eventually circle the entire universe, allowing observers to see multiple images of the same distant objects from different epochs of cosmic history. This cosmic hall of mirrors would reveal the universe at different ages, creating a complex tapestry of past and present visible in a single sky. The mathematics describing these topologically complex universes relates to the concept of quotient spaces. Mathematicians start with ordinary flat, infinite space, which they call E3, and then identify certain points as being the same, effectively gluing regions together to create connectivity. The resulting quotient space, E3G, where gamma represents the specific identifications, can be finite in volume while maintaining locally flat geometry. The three-dimensional torus, one of the simplest such spaces, results from identifying opposite faces of a cube. Imagine a cosmic cube where leaving through the right face brings you in through the left, leaving through the top brings you in through the bottom, and leaving through the front brings you in through the back. Within this cube, space would appear completely normal and flat, but the universe would contain only the volume of the cube, repeated in a never-ending pattern. This arrangement creates a universe with no center and no boundary, yet containing a finite amount of space. The cosmic cube is not a literal cube embedded in some higher dimensional space, but a way of describing the connectivity of three-dimensional space itself. The identifications of opposite faces create a flat, finite universe that wraps around in all three dimensions. More complex topologies are possible, involving twists and turns in how different regions connect. The three-dimensional Klein bottle, for instance, includes a flip in orientation when passing through certain boundaries, creating a universe with strange global properties despite being locally flat. Some of these exotic topologies would create observable effects even within our current cosmic horizon. They might produce specific patterns in the cosmic microwave background, or create multiple images of distant quasars. The absence of such clear signatures in current data constrains, but does not eliminate the possibility of a multi-connected universe. The question of cosmic topology connects to deeper issues in physics and cosmology. Why does the universe have the dimension and geometry it does? Why 3 dimensions of space and 1 of time? Why the particular fundamental forces and particles we observe? These questions touch on the limits of current theory and may require new approaches that unify general relativity with quantum mechanics. Various theories of quantum gravity, including string theory, suggest that space itself might emerge from more fundamental structures. In these frameworks, the dimension, geometry, and topology of the universe are not arbitrary, but arise from underlying principles. Some versions of string theory even require additional dimensions beyond the four of spacetime, with these extra dimensions compactified or curled up so tightly that they're undetectable in everyday experience. If the universe does have a multi-connected topology, it might reflect processes in the very early universe, perhaps even before inflation. The particular pattern of identifications might be a fossilized relic of quantum fluctuations in the primordial cosmos, a kind of topological DNA that shaped all subsequent evolution. This possibility links the question of cosmic topology to the broader mystery of initial conditions. Why did the universe begin in the particular state it did? Was this state random, chosen from among countless possibilities, or determined by some deeper principle? If the universe is finite in volume due to its topology, does this constrain the range of possible initial configurations? These questions remain open at the frontier of theoretical cosmology. While observations currently suggest a flat universe extending beyond our observable horizon, they cannot definitively determine whether space is truly infinite or merely very large but finite due to an exotic topology. Another intriguing aspect of a flat yet finite universe involves cosmic expansion. In the standard cosmological model, the expansion of the universe refers to the increasing separation between galaxies due to the stretching of space itself. This expansion can occur regardless of whether space is finite or infinite. In a finite universe with the topology of a three-dimensional torus, the expansion would increase the volume of the cosmic cube over time, with the identification of opposite faces maintained throughout. Observers within this expanding torus would see the same pattern of galactic recession that we observe in our universe. Such a universe could still undergo accelerated expansion driven by dark energy. The finite volume would grow exponentially, with the space between galaxies stretching just as in an infinite cosmos. The critical difference is that the total volume, while increasing without bound, would remain finite at any given time. This distinction might seem academic, but it has implications for the very long-term future of the universe. In an infinite cosmos expanding forever, the total amount of disorder or entropy can increase without limit. In a finite universe, even an expanding one, the total possible entropy at any given time has an upper bound, though this bound increases as the universe expands. These considerations connect to profound questions about the beginning and end of time. If the universe is finite in space due to its topology, might it also be finite in time? Could the accelerated expansion eventually reach a limit, perhaps triggering a collapse or transition to a new phase? While current observations suggest eternal expansion, the ultimate fate of a topologically complex universe might include possibilities beyond our current theoretical understanding. The concept of a flat yet finite universe also affects how we think about the multiverse. The idea that our observable cosmos might be just one bubble in a vast ensemble of universes, each with potentially different physical laws. If space has a multi-connected topology, the volume available for other universes might be constrained, influencing the landscape of possibilities. From a philosophical perspective, a flat yet finite universe offers a middle ground between the conceptual problems of both infinite and bounded spaces. Unlike a truly infinite cosmos, it doesn't imply infinitely repeated structures and beings. Unlike a positively curved finite universe, it maintains the familiar Euclidean geometry we associate with flat space. It provides closure without an edge, finitude without a boundary. This elegant solution to the problem of cosmic architecture has historical precedents. Ancient Greek philosophers debated whether space could be truly infinite, with some arguing that infinity was a mathematical abstraction that couldn't correspond to physical reality. Medieval cosmologists imagined a finite universe bounded by the sphere of fixed stars, with complex questions about what might lie beyond. Modern cosmology has transformed these ancient questions through precise observations and mathematical models. We now know that the universe is expanding, that it began in a hot, dense state about 13.8 billion years ago, and that it appears flat to the limits of our measurement. The possibility that this flat space might be finite due to its topology represents a sophisticated resolution to questions that have puzzled humanity for millennia. To search for evidence of a multi-connected universe, cosmologists analyze the cosmic microwave background for signs of repeated patterns or matched circles. They examine catalogs of distant quasars and galaxies, looking for multiple images of the same object seen from different angles. They develop statistical methods to detect subtle signatures that might reveal cosmic connectivity. Future observations may provide more definitive answers. The next generation of cosmic microwave background experiments, with greater sensitivity and resolution, might detect topological signatures currently beyond our reach. Advanced surveys of the large-scale structure of the universe could reveal patterns consistent with a multi-connected topology. Gravitational wave astronomy might even detect signals that have traveled along different paths through a topologically complex cosmos. For now, the question remains open. The universe appears flat within our observable horizon, but whether this flat space extends infinitely or loops back on itself in a finite volume remains unknown. Both possibilities are consistent with current observations and with the mathematical framework of general relativity. This uncertainty exemplifies the provisional nature of scientific knowledge. We develop models based on available evidence, fully aware that future observations may reveal new aspects of reality. The universe often proves more subtle and complex than our initial theories suggest, rewarding continued exploration with deeper understanding. If the universe does indeed have a multi-connected topology, making it flat yet finite, it would represent one of the most elegant solutions to the ancient question of cosmic architecture. Rather than an infinite expanse or a bounded realm with an edge, we would inhabit a space that wraps around itself, containing a finite volume within a boundary-less structure. Such a universe would be both comprehensible and mysterious. Its local geometry would follow the familiar rules of Euclidean space, with light traveling in straight lines and parallel beams remaining parallel. Yet its global structure would create connections across vast cosmic distances, potentially allowing light to circle the entire universe, creating multiple images of the same distant objects. This possibility reminds us that flatness in cosmology does not necessarily imply the infinite expanse we might intuitively associate with Euclidean geometry. The global topology of space can create finite volumes with no boundary, challenging our everyday understanding, while revealing the subtle mathematics that underlies physical reality. As we contemplate this possibility, we are reminded of the limitations of human perception and the power of mathematical reasoning to expand our understanding beyond what we can directly observe. The universe may be structured in ways that seem counterintuitive, yet follow precise mathematical principles. Our cosmic home might be both flat and finite, both boundary-less and contained, both familiar in its local geometry and surprising in its global connectivity. Flat doesn't always mean forever. It could mean connected. The universe might extend not infinitely in all directions, but rather wrap around itself in a complex topological pattern, creating a finite yet boundary-less cosmos. This elegant possibility, consistent with current observations yet extending beyond our observable horizon, reminds us that reality often exceeds our imagination, revealing structures more subtle and beautiful than we initially conceived. Even a flat plane can float in something vast, something hidden. As we contemplate the evidence suggesting our universe is remarkably flat, we should remember that flatness represents just one possibility in a rich landscape of potential cosmic geometries. The mathematics of modern physics allows for shapes and structures far stranger than the simple curved or flat spaces we've considered so far. Our universe might have extra dimensions, exotic topologies, or geometrical features that extend beyond the 4 dimensions of spacetime we directly experience. Even if our observable cosmos appears flat, this flatness might be embedded within a larger, more complex reality, whose full geometry remains hidden from our view. One of the most fascinating possibilities involves extra dimensions beyond the familiar 3 of space and 1 of time. String theory, a leading candidate for a unified description of all physical forces, typically requires 10 or 11 dimensions for mathematical consistency. If these theories correctly describe nature, where are these additional dimensions, and why don't we notice them in everyday experience? The most common explanation is that the extra dimensions are compactified, curled up so tightly that they're undetectable at ordinary energies. Imagine an ant walking along a garden hose. From far away, the hose appears one-dimensional, a simple line, but the ant experiences two dimensions, moving both along the hose and around its circumference. Similarly, our apparently three-dimensional space might have additional dimensions curled up at each point, too small to notice in ordinary experience, but fundamentally altering the underlying physics. These compactified dimensions could take various geometrical forms, from simple circles to complex shapes called Calabi-Yau manifolds. The particular configuration of these hidden dimensions would determine many properties of our observable universe, including the types of particles that exist and the forces through which they interact. Different arrangements of the extra dimensions could create entirely different physical realities, a concept that forms the basis for the string theory landscape, with its vast number of possible universes. If extra dimensions do exist, they might not all be microscopic. Some theories propose large extra dimensions that could be detected through their gravitational effects. Gravity might spread into these additional dimensions, explaining why it appears so much weaker than the other fundamental forces. Experiments at particle accelerators like the Large Hadron Collider have searched for evidence of these large extra dimensions, so far without success, but the possibility remains open. Another intriguing framework involving alternative geometries is brane cosmology, which emerges from string theory. In this picture, our entire observable universe exists on a brane, a kind of membrane embedded in a higher dimensional space called the bulk. Other branes might exist within this bulk, potentially with their own three-dimensional universes complete with stars, galaxies, and perhaps even life. The interactions between these branes could explain various cosmic phenomena. Some versions of brane cosmology propose that the Big Bang resulted from a collision between branes, with the tremendous energy of this impact initiating our universe's expansion. Others suggest that dark energy, the mysterious force driving cosmic acceleration, might involve gravitational effects leaking from other branes or from the bulk itself. If our universe does exist on a brane, the flatness we observe might be a local property of our particular membrane, independent of the geometry of the larger bulk space. Just as a flat sheet of paper can be embedded in curved three-dimensional space, our apparently flat cosmos might float within a higher dimensional reality with its own complex geometry. This possibility connects to what physicists call the embedding problem in general relativity. Einstein's equations describe the intrinsic curvature of spacetime, how it curves within itself, but they don't specify how our four-dimensional reality might be embedded in a higher dimensional space. Different embeddings could preserve the same intrinsic geometry while creating different relationships with whatever might exist beyond our observable universe. Beyond extra dimensions, theoretical physics allows for even more exotic cosmic geometries through the mathematics of non-commutative geometry. In ordinary space, it doesn't matter in which order you move, first north and then east, or first east and then north, you'll reach the same destination. But in non-commutative spaces, the order of operations matters, creating geometries that defy our intuitive understanding. These unusual mathematical structures might seem abstract, but they could be relevant to quantum gravity, the elusive theory that would unify general relativity with quantum mechanics. At the Planck scale, about 10 to the power of negative 35 meters, space-time might exhibit quantum fuzziness that breaks the assumptions of classical geometry. Non-commutative geometry provides a framework for describing such a quantum spacetime. Another alternative to simple flatness or curvature involves what mathematicians call non-metrical geometry, where the concept of distance itself becomes more complex than in ordinary space. In fractal geometries, for instance, the measured distance between points depends on the resolution of measurement, with finer scales revealing ever more intricate structure. Some physicists have proposed that space-time might have fractal properties at very small scales, creating a geometry that looks smooth and ordinary at human scales, but becomes increasingly complex as we probe smaller distances. Moving from the very small to the very large, cosmologists have also considered anisotropic universes, where space has different properties in different directions. Unlike the isotropic cosmos assumed in standard models, where space looks the same in all directions, an anisotropic universe might expand at different rates along different axes or have different curvatures in different planes. While observations of the cosmic microwave background strongly constrain such anisotropy, suggesting the universe is remarkably isotropic on large scales. Some anomalies in the CMB data hint at possible deviations from perfect isotropy. These include the so-called axis of evil, an apparent alignment of features in the CMB that seems to define a preferred direction in space. Whether these anomalies represent genuine cosmic anisotropy or statistical flukes remains an open question. Beyond specific alternative geometries, theoretical physics raises the possibility of dynamical topology, where the connectedness of space itself might change over time or in different regions. In quantum gravity, approaches like causal set theory or causal dynamical triangulations, the fundamental structure of spacetime emerges from discrete elements and their relationships, potentially allowing for topological transitions that would be impossible in classical general relativity. Some cosmologists have even explored the idea of a multi-connected universe with mixed curvature, where different regions might have positive, negative, or zero curvature connected through complex topological structures. Such a universe would appear different to observers in different locations, challenging the cosmological principle that the universe is homogeneous and isotropic on the largest scales. These alternative geometries might seem speculative, but they emerge naturally from attempts to develop a complete theory of quantum gravity or to explain observed features of our universe. They remind us that cosmic flatness, while supported by current evidence, represents just one possibility in a rich landscape of potential structures allowed by the mathematics of modern physics. The ultimate nature of space might involve a harmonious synthesis of different geometrical features, with flatness on observable scales emerging from more complex structures at smaller or larger scales. Just as the apparently flat surface of a calm lake consists of water molecules in constant motion, or the flat screen displaying these words consists of pixels with their own internal structure, the flatness of our cosmos might conceal deeper levels of geometrical complexity. This layered view of cosmic geometry aligns with the holographic principle, a radical idea that emerged from the study of black holes. According to this principle, all the information contained in a volume of space can be encoded on its boundary surface, like a three-dimensional hologram projected from a two-dimensional image. This suggests that our three-dimensional reality might be a projection of processes occurring on a distant two-dimensional surface. The most developed version of this idea is the ADS-CFT correspondence, proposed by Juan Maldacena in 1997. This mathematical relationship connects a gravitational theory in a space with negative curvature, called anti-de Sitter space, to a quantum field theory without gravity on the boundary of that space. While our universe appears to have zero or slightly positive curvature, rather than the negative curvature of anti-de Sitter space, the holographic principle might still apply in some form, suggesting that our apparently flat spacetime might emerge from more fundamental structures. These theoretical explorations remind us that flatness, curvature, and other geometrical properties might not be fundamental but emergent, arising from deeper principles or structures that we're only beginning to understand. The shape of the universe might not be given a priori, but dynamically determined through physical processes, perhaps involving quantum fluctuations in the early cosmos or interactions with dimensions or regions beyond our direct observation. Some approaches to quantum gravity, including loop quantum gravity and tensor network models, suggest that spacetime itself is not fundamental, but emerges from more basic quantum entities and their relationships. In these frameworks, the familiar geometry of Einstein's general relativity, including the concept of flatness, would be an approximate description valid only at scales much larger than the Planck length. This emergent view of geometry has philosophical implications, challenging the Kantian notion that space is an a priori form of intuition, a mental framework we impose on experience. Instead, spatial relationships might emerge from more fundamental processes, with different geometries becoming relevant at different scales or in different regimes. The possibility of alternative cosmic geometries extends beyond theoretical speculation to empirical research. Astronomers continue to analyze the cosmic microwave background and the large-scale distribution of galaxies for hints of exotic topologies or geometries. Physicists design experiments to detect extra dimensions through their gravitational effects or to probe the quantum nature of spacetime at increasingly small scales. future observations might reveal unexpected geometrical features currently hidden by the limitations of our instruments or analyses. The continuing tension in measurements of the Hubble constant, the rate of cosmic expansion, might indicate new physics beyond the standard cosmological model, potentially including novel geometric structures. Gravitational wave astronomy, still in its infancy, could eventually detect signals that have traveled along different paths through a topologically complex cosmos. While current evidence suggests that our observable universe is remarkably flat, the door remains open to more complex geometries at scales beyond our current reach, or in dimensions beyond the familiar 4 of spacetime. The flatness we observe might be like the apparent flatness of Earth's surface to someone standing on a beach, a local property that gives way to more complex global structure when viewed from a broader perspective. The idea that our flat universe might be embedded in a higher dimensional space or might emerge from more fundamental quantum structures resonates with ancient philosophical questions about the nature of reality. Plato's allegory of the cave, where prisoners mistake shadows for reality, reminds us that what we perceive might be projections of a deeper truth. Eastern philosophical traditions, with concepts like Maya in Hinduism or Sunyata in Buddhism, similarly suggest that apparent reality might conceal more fundamental levels of existence. Modern physics gives mathematical precision to these philosophical intuitions, describing how our observable universe might relate to larger or more fundamental structures. While we cannot directly observe extra dimensions or quantum spacetime, we can develop mathematical models that make testable predictions, gradually refining our understanding of how alternative geometries might manifest in observable phenomena. Throughout this exploration of cosmic shape, we've moved from the simple question of whether the universe is flat, positively curved, or negatively curved to a richer landscape of possibilities involving exotic topologies, extra dimensions, and emergent geometries. This progression reflects the development of physics itself, from Euclidean geometry to non-Euclidean spaces, from classical general relativity to quantum approaches to spacetime. What unifies these diverse possibilities is the power of mathematics to describe structures beyond our direct experience. The same mathematical principles that allow us to calculate the orbit of a planet or the trajectory of a spacecraft can be extended to describe spaces with additional dimensions or complex topologies. This mathematical continuity gives us confidence that even the most exotic theoretical proposals remain connected to the empirical world through testable predictions. As we consider these alternative shapes and geometries, we should remember that our quest to understand the cosmos involves both theoretical exploration and empirical observation. Mathematical models propose possibilities, but nature determines which of these possibilities is realized in our universe. The interplay between theory and observation drives scientific progress, with each informing and constraining the other. The current evidence pointing toward a flat universe represents a remarkable convergence of theory and observation. The cosmic microwave background, the distribution of galaxies, and other lines of evidence all suggest that our observable universe follows Euclidean geometry with extraordinary precision. This flatness aligns with the predictions of cosmic inflation. The theory that the early universe underwent a period of exponential expansion that would naturally flatten any initial curvature. Yet this observed flatness doesn't preclude more complex geometries beyond our horizon or in dimensions beyond the familiar 4 of spacetime. The universe might be both flat and finite through an exotic topology, both simple in its observable geometry and complex in its full structure, both familiar in what we can measure and surprising in what remains hidden. This layered understanding of cosmic geometry reflects our evolving comprehension of nature itself. Throughout history, scientific revolutions have revealed that reality extends beyond our immediate perception, from the microscopic world of atoms and cells to the cosmic reaches of distant galaxies. Each new level of understanding hasn't invalidated earlier knowledge, but has placed it within a broader context, showing how familiar phenomena emerge from deeper structures. In a similar way, the flatness we observe in our cosmic neighborhood might emerge from a more complex underlying reality, a geometry that includes additional dimensions, exotic topologies, or quantum structures beyond classical spacetime. This possibility reminds us that science remains an ongoing journey of discovery, with each answer raising new questions that lead us deeper into the mysteries of existence. As we drift through these alternative cosmic shapes, we might wonder about the meaning of it all. Why should the universe have any particular geometry? Is the structure of space arbitrary, one possibility among countless others, or determined by some deeper principle that makes it necessary rather than contingent? Various theoretical approaches suggest different answers to these questions. String theory, with its landscape of possible universes corresponding to different configurations of extra dimensions, might imply that our universe's geometry is just one realization among many, perhaps selected through a process like cosmic inflation or eternal inflation that creates a multiverse of bubbles with different properties. Other approaches, seeking more uniqueness in fundamental theory, suggest that the true equations of quantum gravity might have a unique solution or a very limited set of solutions, making the geometry of our universe necessary rather than arbitrary. In this view, the apparent flatness of our cosmos would reflect deeper mathematical principles that constrain how reality can be structured. Between these positions lies the anthropic perspective, which notes that only certain geometries and physical laws allow for the emergence of complex structures like stars, planets, and ultimately life. In a multiverse with diverse properties, we necessarily find ourselves in a region compatible with our existence. The flatness we observe might be partly explained by the fact that significantly curved spaces would expand or recollapse too quickly for stars and galaxies to form, precluding the development of observers like ourselves. These different perspectives on cosmic geometry complement rather than contradict each other, offering various levels of explanation for the structure we observe. The mathematical consistency of physical theory, the dynamical processes of cosmic evolution, and the conditions necessary for complexity and life all contribute to our understanding of why the universe takes the shape it does. As we continue to explore alternative cosmic geometries, we participate in humanity's oldest intellectual adventure, the quest to understand the fundamental nature of reality. From ancient cosmologies with their celestial spheres to modern theories of quantum gravity, this quest has driven the development of both science and philosophy, expanding our perspective beyond immediate experience to encompass the structure of the cosmos itself. Though our individual lives occupy just a tiny fraction of cosmic history, and our bodies fill an infinitesimal portion of cosmic space, our minds can grasp the geometry of the entire observable universe and contemplate structures that extend beyond our direct perception. This cognitive reach, this ability to understand reality beyond our immediate experience, represents one of the most remarkable aspects of human existence. The flatness we observe in our cosmic neighborhood, combined with the theoretical possibility of more complex geometries beyond, reminds us of both the power and limitations of human understanding. We can measure the curvature of the universe with extraordinary precision, yet we remain open to the possibility that this observed flatness exists within a larger, more complex reality whose full structure continues to elude us. In this ongoing exploration of cosmic shape, we find a balance between knowledge and mystery, between what we can measure and what remains beyond our reach. The universe appears flat to the limits of our observation, yet this flatness might float within something vaster and more complex, a higher dimensional space or a quantum reality that we glimpse only indirectly through mathematical models and their testable predictions. Even a flat plane can float in something vast, something hidden. Our apparently flat universe, extending in 3 dimensions of space and 1 of time, might be embedded in a higher dimensional bulk, might emerge from quantum structures beneath space-time itself, or might connect back on itself through exotic topology to form a finite yet boundless cosmos. These possibilities remind us that flatness, while supported by current evidence, might be just one aspect of a richer cosmic geometry whose full complexity continues to inspire both scientific research and philosophical reflection. To ask if space is flat is to ask what it means to exist at all. Throughout our journey exploring the geometry of the cosmos, we've examined evidence from the cosmic microwave background, studied the distribution of galaxies, and contemplated the mathematics of curved spacetime. We've considered the possibility of a flat yet finite universe through exotic topology and imagined alternative geometries involving extra dimensions or quantum structures. These scientific inquiries tell us what the universe is and how it behaves. But now let us turn to the deeper question: why does the shape of the universe matter? What does cosmic geometry tell us about the meaning of existence and our place within the great pattern of reality? The shape of space isn't merely a scientific curiosity, but touches on profound philosophical questions that have engaged minds throughout human history. The geometry of the cosmos influences our understanding of infinity, necessity, unity, and even the nature of knowledge itself. It shapes how we conceive of beginnings and endings, boundaries and limitlessness, the one and the many. Let us begin with infinity, that concept both mathematical and mystical that has haunted human thought since ancient times. A flat universe, extending endlessly in all directions, embodies one form of the infinite, the boundless expanse without limit. This spatial infinity challenges our finite minds, which evolved to comprehend the medium-scale world of our immediate environment. We can represent infinity mathematically, but can we truly grasp it intuitively? The Greek philosopher Anaximander, in the 6th century BCE, spoke of the apeiron, the boundless or infinite from which all things emerge and to which they return. For him, infinity was not just spatial, but metaphysical, the underlying reality beyond specific forms. The Pythagoreans, by contrast, were uncomfortable with infinity, preferring the finite and determinate, which they associated with beauty and order. This tension between infinite and finite conceptions of reality continues in our modern cosmological debates about whether the universe is boundless or limited, whether through curvature or topology. If the universe is truly infinite in extent, containing infinitely many galaxies, stars, and planets, then everything physically possible exists not just once, but infinitely many times. In an infinite cosmos governed by the same physical laws throughout, the arrangement of matter in our observable universe, limited by the constraints of those laws, would necessarily repeat beyond our cosmic horizon. This would include exact duplicates of Earth and all its inhabitants, living out every possible variation of our history. This concept of cosmic repetition due to infinity appears in Friedrich Nietzsche's idea of eternal recurrence and has found mathematical expression in modern cosmology. But does such repetition diminish the significance of our individual existence? If there are infinite copies of you reading these words right now, having exactly the same thoughts and experiences, what does that mean for the uniqueness of your consciousness, your identity, your choices? Conversely, if the universe is finite, either through positive curvature or exotic topology, it contains only a limited amount of matter arranged in a finite number of possible configurations. Such a cosmos might seem more comprehensible, more in line with our intuitive sense of bounded wholes, but it raises its own philosophical questions. Why this particular size and not another? Why these specific contents and not different ones? A finite universe seems more contingent, more in need of explanation for its particular characteristics. This leads us to questions of necessity and contingency that have occupied philosophers from Aristotle to Leibniz. Is the geometry of our universe necessary, determined by mathematical principles that could not be otherwise? Or is it contingent, one possibility among many that happens to be realized in our cosmos? Different approaches to fundamental physics suggest different answers. String theory, with its landscape of possible universes corresponding to different configurations of extra dimensions, implies a kind of contingency. Our universe's geometry would be just one realization among many, perhaps selected through cosmic inflation or eternal inflation, creating a multiverse of bubbles with different properties. This view aligns with Leibniz's question of why there is something rather than nothing, and why this something rather than another, suggesting that perhaps all mathematical possibilities are physically realized somewhere in the multiverse. Other approaches to quantum gravity seek more uniqueness, suggesting that the true equations might have a single solution or a very limited set of solutions. This would make the geometry of our universe necessary rather than arbitrary, reflecting deeper mathematical principles that constrain how reality can be structured. Such a view harmonizes with Spinoza's conception of a necessary being whose nature could not be otherwise, or with Einstein's question about whether God had any choice in creating the universe. Between these positions lies the anthropic perspective, which notes that only certain geometries and physical laws allow for the emergence of complex structures like stars, planets, and ultimately life. In a multiverse with diverse properties, we necessarily find ourselves in a region compatible with our existence. This view doesn't make our universe's properties necessary in an absolute sense, but conditional on the existence of observers, a position with echoes in Kant's understanding of how the structure of human cognition shapes our experience of reality. The shape of the universe also relates to ancient questions about unity and multiplicity. Is the cosmos fundamentally one thing, a unified whole with various manifestations, or is it many distinct things in relationship? A positively curved, finite universe has a kind of unity, being completely self-contained, with no boundary or exterior. A flat, infinite universe might seem more aligned with multiplicity, containing endless variations without encompassing them in a single closed form. Yet even an infinite universe follows unified laws and exhibits patterns that repeat across vast distances. The cosmic microwave background, nearly identical in temperature in all directions, suggests a fundamental unity beneath the apparent diversity of cosmic structure. This interplay between the one and the many, between unity and diversity, appears in philosophical traditions worldwide, from Parmenides and Heraclitus in ancient Greece to Advaita Vedanta in India. The topology of the universe adds another dimension to these reflections. If the cosmos is multi-connected, with space looping back on itself through exotic topology, it would be both unified and complex, both finite and boundary-less. Such a structure might offer a geometric reflection of philosophical notions of interconnectedness, where apparent separateness conceals deeper unity. This idea of hidden connectedness appears in many wisdom traditions. Buddhism speaks of dependent origination, where all phenomena arise in mutual dependence. Indigenous philosophies worldwide emphasize the interconnectedness of all beings. Modern ecology reveals the intricate web of relationships that sustain ecosystems. A universe with complex topology, where distant regions connect through cosmic shortcuts, provides a striking geometric analog to these philosophical insights. Beyond questions of infinity, necessity, and unity, the geometry of the cosmos touches on epistemological concerns about the limits of human knowledge. How can we, limited beings in a tiny region of space-time, know the shape of the entire universe? Our observations extend only to our cosmic horizon, about 46 billion light-years in radius. What lies beyond remains inference, based on theoretical models and the assumption that physical laws remain constant throughout space. This limitation highlights the dynamic between empirical observation and theoretical reasoning that characterizes scientific knowledge. We observe the cosmic microwave background and the distribution of galaxies, measuring the apparent flatness of space within our observable universe. But to understand what this means for the cosmos as a whole, we must rely on mathematical models that extend beyond direct observation. Immanuel Kant distinguished between phenomena, things as they appear to us, and noumena, things as they are in themselves, independent of our perception. The full geometry of the universe, especially regions beyond our cosmic horizon or extra dimensions beyond the familiar four of space-time, might represent a kind of noumenon, a reality we can approach through mathematics but never directly observe. This perspective suggests humility about our cosmic knowledge. While we can determine with remarkable precision that the observable universe is flat to within a few tenths of a percent, the complete shape of the cosmos, including regions forever beyond our view, remains partly speculative. Science gives us increasingly accurate models of reality, but these models remain human constructions, attempts to grasp a universe that always exceeds our full comprehension. Yet there is something profound in the fact that we can know as much as we do. Through mathematics and careful observation, we've determined the age of the universe, mapped its large-scale structure, and measured its geometry. Despite our physical insignificance in the cosmic vastness, our minds can grasp patterns and principles that govern reality at the largest scales. This cognitive reach, this ability to understand beyond our immediate experience, represents one of the most remarkable aspects of human existence. The shape of the universe also relates to our understanding of time and history. A positively curved universe that eventually recollapses in a big crunch suggests a cosmic cycle with a definite end. a flat or negatively curved universe that expands forever, gradually cooling toward heat death, implies a linear trajectory with no return. These different cosmic futures resonate with diverse cultural conceptions of time, from the cyclic time of many ancient civilizations to the linear time of modern Western thought. The discovery of dark energy, driving accelerated cosmic expansion, has shifted our understanding toward eternal expansion regardless of geometry. But questions remain about the ultimate fate of the cosmos. Will expansion continue forever, creating an increasingly vast and empty universe? Will dark energy eventually change its behavior, perhaps triggering a big rip where even atoms are torn apart, or a big bounce leading to a new cycle of expansion? The shape of space constrains these possibilities, but doesn't uniquely determine them, given our current understanding of dark energy. These questions about cosmic destiny touch on our human need for narrative, for understanding our place within a story that has meaning and direction. Different philosophical traditions offer varied perspectives on this search for meaning in a vast and ancient universe. Existentialist philosophers, like Camus, suggest that we must create meaning ourselves in a universe indifferent to human concerns. Religious traditions find purpose in cosmic design or divine participation in history. Indigenous wisdom often locates meaning in the web of relationships between all beings, human and non-human. The scientific narrative of cosmic evolution, from the Big Bang through the formation of galaxies, stars, planets, and eventually life, offers its own kind of meaning. It connects us to the universe not as strangers in an alien reality, but as participants in an ongoing process of emergence and development. The atoms in our bodies were formed in ancient stars. The complexity of our brains evolved through billions of years of life on Earth. We are not separate from the cosmos, but expressions of its creative unfolding. In this context, the shape of the universe becomes part of our understanding of the conditions that allowed for our existence. A universe with drastically different geometry might not permit the formation of galaxies, stars, and planets necessary for life as we know it. The apparent flatness of our cosmos, likely established by inflation in its earliest moments, created the stage upon which the drama of cosmic evolution has played out. This perspective offers what philosopher Thomas Nagel calls the view from nowhere, an attempt to see ourselves objectively as parts of a reality that exists independently of our particular viewpoint. Such cosmic objectivity doesn't negate the subjective meaning of our individual lives, but places it within a larger context, connecting personal significance to universal processes. The shape of the universe also relates to philosophical questions about the nature of space itself. Is space a substance, a kind of container in which objects exist, or is it merely a system of relationships between objects, with no independent existence of its own? These questions echo the debate between Isaac Newton, who advocated absolute space existing independently of its contents, and Gottfried Leibniz, who argued for relational space defined by the positions of objects relative to each other. Einstein's general relativity, which describes the geometry of spacetime as curved by mass and energy, seems to support a relational view. Space isn't a fixed background against which cosmic drama unfolds, but a dynamic participant that both influences and is influenced by matter and energy. The flatness of the universe isn't an intrinsic property, but emerges from the distribution of cosmic contents and their evolution over time. Yet quantum approaches to gravity, which attempt to unify general relativity with quantum mechanics, suggest that spacetime itself might be emergent, arising from more fundamental quantum structures or relationships. Loop quantum gravity, string theory, and other approaches propose different understandings of what lies beneath classical spacetime, potentially including discrete quantum elements, higher dimensional branes, or networks of quantum entanglement. These theoretical developments remind us that our understanding of cosmic geometry continues to evolve. The flat universe revealed by current observations represents our best model based on available evidence. But deeper levels of reality might await discovery, transforming our conception of what space fundamentally is. This ongoing evolution of scientific understanding parallels the philosophical journey from naive realism to more nuanced views of how human cognition interacts with external reality. Throughout this exploration of cosmic shape, we've moved between empirical observation, mathematical modeling, and philosophical reflection. This integration of different ways of knowing mirrors the complementary relationship between science and philosophy throughout history. Science tells us what the universe is and how it behaves, while philosophy explores what this knowledge means for our understanding of existence and our place within reality. As we complete our journey through cosmic geometry, we return to the question that guided us. Does it matter whether the universe is flat? The answer lies not just in the scientific importance of determining cosmic parameters, but in the philosophical insights this knowledge offers. The shape of the universe influences our understanding of infinity and finitude, necessity and contingency, unity and multiplicity. It shapes our cosmic narrative and informs our conception of where we stand in the great pattern of existence. To ask if space is flat is to ask what it means to exist at all. It is to inquire into the structure of reality itself, the fabric within which all beings and events are woven. It is to seek our place within the cosmic tapestry, understanding how our individual lives connect to the universe's vast expanse in space and time. The flat universe revealed by our instruments is not just a scientific fact, but a philosophical invitation to contemplate the nature of reality and the meaning of our presence within it. Whether the universe is precisely flat or has subtle curvature, whether it extends infinitely or loops back on itself through exotic topology, whether it contains extra dimensions or emerges from quantum structures beneath space-time, it remains our cosmic home, the arena of our existence and the source of our being. In seeking to understand its shape, we deepen our connection to the reality we inhabit, recognizing ourselves as both observers of the cosmos and expressions of its creative unfolding. To ask if space is flat is to ask what it means to exist at all. Flat, curved, infinite, finite. The universe is not just what we see, but how we ask. Sleep now under a sky shaped by time, by light, and by wonder. We may never know its true form, but we are part of it, and it a part of us. Our journey through the geometry of the cosmos draws to a close. We've explored the meaning of flatness, the nature of curved space, the behavior of light across cosmic distances, and the mathematics of Einstein's general relativity. We've examined the evidence from the cosmic microwave background, considered the implications of inflation, and contemplated alternative shapes and topologies. We've reflected on what cosmic geometry tells us about the origin of the universe and its ultimate fate, about quantum fields in empty space, and about the limits of human perception and understanding. What emerges from this exploration is a picture of extraordinary elegance and simplicity, a universe that appears flat to the limits of our measurement, with any curvature so slight that it would only become apparent across distances far larger than our cosmic horizon. This flatness, likely established by inflation in the earliest moments after the Big Bang, created the stage upon which all subsequent cosmic evolution has unfolded. Yet this apparent simplicity conceals deeper layers of complexity and mystery. Our flat observable universe might be embedded in a higher dimensional bulk, might connect back on itself through exotic topology, or might emerge from quantum structures beneath spacetime itself. The flatness we measure might be just one aspect of a richer cosmic geometry whose full nature continues to elude us. This interplay between what we know and what remains beyond our knowledge characterizes the scientific quest to understand the universe. Each answer achieved through observation and theory leads to new questions that push the boundaries of our understanding. The flat universe revealed by our instruments is both a remarkable achievement of human ingenuity and an invitation to further exploration. As we gaze at the night sky, seeing stars whose light has traveled across vast distances to reach our eyes, we participate in humanity's oldest intellectual adventure, the quest to comprehend the cosmos we inhabit. From ancient stargazers tracking celestial motions to modern cosmologists mapping the cosmic microwave background, this quest has driven the development of both science and philosophy, expanding our perspective beyond immediate experience to encompass the structure of reality itself. Though we are tiny beings on a small planet orbiting an ordinary star in one galaxy among billions, our minds can grasp the geometry of the entire observable universe and contemplate structures that extend beyond our direct perception. This cognitive reach, this ability to understand reality beyond our immediate experience, represents one of the most remarkable aspects of human existence. The evidence suggests that we live in a flat universe extending perhaps infinitely in all directions, governed by elegant mathematical laws that allow for the emergence of structure, complexity, and ultimately consciousness. Within this vast cosmos, our planet orbits its star in a dance choreographed by the curvature of space-time, while light from distant galaxies follows geodesics through the cosmic fabric, bringing us news of events billions of years in the past. This scientific understanding doesn't diminish the wonder of existence, but enriches it, revealing patterns and connections invisible to direct perception. The stars we see at night aren't just points of light, but thermonuclear furnaces like our Sun, many of them orbited by planets potentially similar to Earth. The space between galaxies isn't empty, but filled with quantum fields in constant fluctuation. The apparent stability of our world emerges from dynamic processes at every scale, from subatomic particles to cosmic expansion. As we complete our journey, we should remember that our understanding of cosmic geometry, like all scientific knowledge, remains provisional and incomplete. Future observations may reveal subtle features currently beyond our detection. Future theories may reframe our entire conception of what space fundamentally is. The universe has consistently proven more strange and wonderful than our initial theories suggested, rewarding continued exploration with deeper insight. This ongoing journey of discovery connects us to both the past and future of human understanding. We build on the insights of earlier generations of scientists and philosophers, from Euclid and Aristotle to Einstein and Hawking, and we prepare the ground for future explorers who will extend our knowledge beyond its current boundaries, perhaps revealing aspects of cosmic geometry we cannot yet imagine. In this great chain of understanding, each generation contributes its part, gradually refining our picture of the universe through observation, theory, and reflection. The modern evidence for a flat cosmos represents one milestone in this ongoing journey, a testament to what we can achieve through collaborative human effort across cultures and centuries. As you drift towards sleep, consider your place within this vast cosmic tapestry. The atoms in your body were forged in ancient stars. The energy that powers your thoughts traces back to the Big Bang. The mathematical laws that describe cosmic geometry also govern the processes that make your consciousness possible. You are not separate from the universe, but an expression of its creative unfolding, a way for the cosmos to observe and understand itself. Whether the universe is precisely flat or has subtle curvature, whether it extends infinitely or loops back on itself through exotic topology, whether it contains extra dimensions or emerges from quantum structures beneath space-time, it remains our cosmic home, the source of our being and the arena of our existence. In seeking to understand its shape, we deepen our connection to the reality we inhabit. So rest now beneath the canopy of stars, knowing that the apparent void above is not emptiness, but a vibrant geometric structure shaped by matter, energy, time, and the mathematical laws that govern all things. The flat universe we've explored in this journey isn't just a scientific concept, but the very fabric of existence, the medium in which the cosmic drama unfolds. Perhaps, as you close your eyes, you might imagine yourself adrift in this vast cosmic ocean, surrounded by galaxies beyond counting, bathed in the ancient light of the cosmic microwave background. Feel the geometry of space extending in all directions, flat to the limits of measurement, yet potentially connecting back on itself at scales beyond imagination. In this cosmic perspective, our individual concerns find their proper scale, neither negated by the universe's vastness nor detached from its grand processes. We are brief, but real participants in the cosmic story, capable of understanding the very geometry that contains us. Flat, curved, infinite, finite. The universe is not just what we see, but how we ask. Sleep now, under a sky shaped by time, by light, and by wonder. We may never know its true form, but we are part of it, and it a part of us.